concentration of where damage has taken place and where we should be looking first. Once this model has been run, what we'll actually do is we'll look at the most concentrated areas of damage and take a sample of around 500 different buildings. Analysts will then take those samples, they will label that data set, and we will use that data set to fine-tune our model. And this is a really important step in the process because we can take something that might have been delivering 60-65% accuracy because it's a generalized model and really bring that up to 80-85% by the fine-tuning step. And the reason fine-tuning is so important is every context and every country is a little bit different. Buildings in Uganda look different to buildings in London, look different to buildings in Helsinki. And so that fine-tuning step just really helps the model zero in on what kind of structures are present and what damaged and undamaged buildings would look like. Once that process is completed and we've identified our sample area, we fine-tuned the model, we run the final model, and the output of that is essentially, you can see there a comparison between the UNISAT assessment, so the human assessment versus the AI-assisted assessment. You can see the AI assessment has covered a significantly larger number of damaged buildings than what human analysts have identified, so generally identifies a larger portion of buildings more accurately. This then goes through a final verification step, so we will have an analyst look at this, but the time to review this is much quicker than the time to actually build up the data by itself. So we've taken something that would normally take a team of about 14 analysts 10 days, and we've brought that down to under 2 days. Now, I think really important to call out is, again, that none of these solutions were built in isolation. It wasn't our team that built them by ourselves. Partnership is really what is key to the work that we do. And we've collaborated with over 20 partners over the last 2 years of Dish's existence. Everything from technology, data, and funding partners, but most importantly, the humanitarian organizations that we work with, who are the beneficiaries of our products, but who actually deliver services to the true beneficiaries and individuals who are suffering from the disasters that have struck. Key learnings that we've taken away from this is, of course, we can't do this in a bubble, but what private sector really brings is agility, deep technical expertise, and the ability to mobilize resources at a large scale really quickly. And by sitting in the center, we're hoping to connect that with humanitarian organizations who bring trust and neutrality to the table. So by combining the strengths, we hope that this is where innovation meets legitimacy and where we can really deliver responsible impact at scale and do that in a very meaningful way. So you might be thinking, how does the space and AI ecosystem really support real-world impact? And you can see there are a number of ways that we've engaged with partners, everything from data and Earth observation providers to partners who are actually providing us with the models or the technology builds. We do everything in collaboration. And then, of course, funding and delivery partners being incredibly important for us as well. I know I've gone through that very quickly. I apologize, 12 minutes is pretty tight. There's a lot more to talk about, but I believe we have some time for questions. And please do take a photo of our details. If you have any questions, if you want to reach out, myself and Tapio, who's sitting here in the audience, would be very happy to speak to you. Tapio is actually based in Helsinki, so our UN Global Pulse Finland office. So yeah, please reach out. Thank you.
Thank you, Andro. Very inspiring presentation. Any questions from the audience?
Thanks. It sounds like your optical workflow for the Sky model is actually pretty well developed. I'm curious what the next iteration or what the next steps are, and if you're planning to use any SAR data for after natural disasters that might have lots of cloud cover where optical imagery can't be captured quickly.
Thank you. It's a very, very good question. So So the workflow, as you say, is pretty much buttoned up for building damage assessment to this point. What we've done is we've taken a step back to see how can we utilize parts of what we've done for other purposes. So the building footprint model we're using for things like shelter mapping right now, so formal and informal settlement shelter mapping. Some of you may be familiar with UNHCR. Some of the largest exercises for mapping shelters haven't been done within the last 10 or so years. And then mapping something like 40 to 50 shelters could take up to a year to do. We're hoping to bring that down to a couple of weeks of work and the ability to map out all the shelters globally. To the second point, using alternative image sources and providers, we're absolutely open to that. We've explored SAR. We haven't really found a partner to work with on that up to this point. But yeah, absolutely. It is a real challenge, and we saw that with Melissa quite recently, where we didn't get really good images because of cloud cover post the disaster for quite a number of days. So yeah, something that penetrates cloud cover would be amazing, but we haven't gotten there yet. Thanks.
Any other questions? Yeah, it's early in the morning still. I have a maybe additional question. How far are we from an operational, almost real-time system that could be used maybe as a platform for law enforcement and governmental organizations?
I mean, in terms of operations, what we're doing is fully operational right now. It's built into the BAU of UNISAT. It is what a number of organizations in the Philippines use already. Catholic Relief Services use our solution on a daily basis. UN OCHA in the Philippines also use it. So it's really operationalized already. I think real time is very relative. It depends on when we're getting data. So with the mobile data, we're getting that day +1. So whatever data we have from yesterday, we will be receiving this morning, processing. So it's not fully real time, it's day +1 data. And when it comes to optical data post-disaster, of course, that's very much dependent on when imagery is available. So the pre-images are pretty much available immediately, so we can start the workflow as soon as a disaster has taken place. But waiting for post-imagery, it's very much weather dependent and availability of images.
Let's give a big hand to Andro. And next up we have Mikko Stralendorf from the Finnish Meteorological Institute. The stage is yours.
Yeah, can I have the... Yeah. Thank you very much and good morning to everybody. So I can pick up from actually Andro's presentation in the sense that what is a challenge to really more use Earth observation is exactly this thing that we are talking about yesterday or days before that in many products. But we have Earth system models nowadays, the weather forecasting comes from them, that actually can also give tomorrow. And my talk is very much about how can we do that, because this is now possible. We have AI, we have in a way a tool that then gives that to us. I want to thank my team, Anni Kröger, Golda Prakasam, Rasmus Strandorf. They are like the ones who actually get to code and have the fun, and I'm just the one to kind of motivate, coordinate, and maybe review them. But the very general thing that we are doing technically is we are using extreme gradient boosting, we are using things to tune that, and then we use Shapley game theory-based SHAP analysis for our results, because that gives the explainable AI. But to be able to do things that we are kind of like achieving, we have experience now from at least 6 different projects, probably hundreds of machine learning models we have already done in this respect. And the point is really that time series need to be at least 5 years long, and there shouldn't be missing values much. But when you want to get to extreme informations, and like Sandro, in a way already, Andro showed us, the disasters, so the extreme actions are many times the things that we are interested in, then actually to have in the training material things that have extremes, over 20 years is usually the point, and then it's better not to miss anything, because the missing value could be the one that something didn't work, and then the extreme wasn't measured. Feature engineering will become important, and for example, for quality control, adding something like that is not necessarily environmental information, latitude and longitude, is a good tool for that. But I will go through a few examples. So Oceanics, so Cryoscope is the project where we work mostly at in the moment, but Oceanics is something where we already finished. That's for ports and the difficult environment of being marine or being land, being in between. And for that, we wanted to do machine learning exercises. We did have great stuff that we had to work for the Azores, so a very kind of like exotic place. I visited it in this project. And there, Praia da Vitória is one of those kind of airports that are close to a port where we could get observation information as our training truth. There are always challenges with this data, and I think this is what I want to highlight by the fact that then in Helsinki, our most important kind of harbor for transport and kind of goods is Vuosaari, and there we have a station that has longer operated and better records. So Praia da Vitória, when you try to get exactly those observations done from an Earth system model, we use something called reanalysis. So kind of the old weather has been rerun by a model. So we have all kinds of kind of environmental state information for this for all over the world. It's coarse resolution. It's 25 kilometers apart or so. That depends on where you are in the world. But you can use those 4 points, for example, around this one station to use just machine learning very kind of simplistically, put all the data in, see what comes out. We have in this case 54 predictors from the ERA5 reanalysis model, and then use all the 4 grid points. Some of them hit the land, some are on the ocean, which is important for this particular thing. And then, we get a model that has a kind of performance of like the correlation coefficient is 67%, explained variance is 80%, not bad at all in a way, but also not like super good. And then you see by the bee swarm picture of this SHAP thing, which parameters have been the most important ones. TCLW is, for example, how much water in water vapor form is in the total column from the bottom to the top of the atmosphere. These kind of things you then see, which are the kind of variables that make that model. In Vuosaari, the same thing, which is maximum wind gust. I forgot to mention that. That is what for a harbor operation or a port is can they use their cranes? How easy is it to get on and off goods? So that's the important variable. In Vuosaari, where we don't have gaps in this time, I think here we have about 11 years to use as training. In the other case, we had something like principally 5 years, but there were so many gaps in it that it is a little less. And then you see how different the result gets when you just have enough information. The kind of explained variance is 96%. So it's super good. This is almost as good as you don't need to observe anything in this place. We could use our weather forecast models to tell what's the state and how it goes forward. But really, the whole idea, this demonstration for a very simple one-point action is just to demonstrate that the principal machine, that when you kind of tie any kind of product or observation time series, and these can be also pictures, so I will have another example soon, that you tie that to this Earth system model information and you get a successful machine learning result from that, then you have the opportunity to use either seasonal forecast, that means like months ahead you can produce data, or then numerical weather prediction, so 15 days forward, for example, from the ECMWF. And tying these together, you actually get higher resolution machine learning forecasts, so tomorrow and day after of the same products that you have. And now I go to the third project in this presentation, Aurora. It's like health in the Baltic and Finnish kind of cities, and there we try to get something like the urban heat island question answered. But here it's good to understand that these reanalysis data sets, they have these, I think, over almost 300 variables available, and then they have the atmosphere with something like 8 or 9 variables and different heights. They are excellent and very good for the atmosphere, but they do have problems here and there. And especially skin temperature, so when a satellite, for example, is in a cloudless situation, the Earth can have the thermal temperature measured. That's the same thing as in models. We use skin temperature as the name. Those are actually quite a lot off. It has to do more with the fact that the Earth system model wants to make sure that the weather is working good, so they then don't kind of like care so much that this interface is exactly correct. And there is really several degrees of error in the reanalysis data sets here. But it is very important to understand that that's not a problem for machine learning. Machine learning in the process will actually learn how to correct. And this is what we do here. And this is an example really that we just finished end of last year, that we have satellite observation, as you can see on the left side in the picture, that there's a lot of gaps because of clouds here and there, but you have these nice kind of differences in different places around this picture. On the right side, you then have the ERA5 land. It's a little bit higher resolution than 25 kilometers. It's 9 kilometers. It's pretty smooth, but you do see some differences. So you want to merge these two things so that you get a gapless but high resolution map like on the left. So all that gray area over land will be actually filled with numbers that fit into the picture. And we can do that in a very kind of knowledgeable way, that we have lots of observation material in Finland and actually Estonia as well, which we can use for the training. In this case, we actually use just training in smaller boxes, so Tampere city and Helsinki city to do this. And yeah, we need two different models in principle. That the 2-meter temperature that you see in this picture on the right is actually what we, of course, are used to having, but skin temperature is, of course, the ground temperature. They are actually a little different. So we have two models, first to gap fill that skin temperature, and then another model to do the 2-meter temperature. In this case, again, about 50 or so ERA5 land surface parameters, and also ERA5, so I think 100 plus in total variables we had. So a lot of them were also these different height, let's say, variables in the atmosphere. We also used a lot of like land cover information, vegetation, and fractions of different land cover that those put in, and then lat longitude as quality check. Day of year, month, and things like this are also important to get that seasonal signal in there by machine learning. 1.4 degrees is what we got as a result for this. And the sharp results here are so that the maximum temperature per day was the most important, then also higher resolution things were important. Day of year is also important, so you get a little bit the drift of how this works. We can explain this. I jump over the 2-meter temperature. Here's now the results of how does it look for a month in 2024, July. And for every day, we now have then temperatures for the afternoon in this case. Yeah, and we can then, with this model, also have forecasts for 15 days or longer forecast. Yeah. The good thing about this project is that we actually will get from new space companies, Aurora Tech and Constellar. They have new satellites flying. Their land surface temperature kind of observations will be available for this year's summer period, so that we can compare then how good does our model work compared to real observations. That will be cool. Have to jump a little bit. That's just these examples of very atmospheric parameters. We have also a project where we did use actually real people in the ground to do observations of how is soil moisture. That will actually be tomorrow in a presentation by Joonas Kolstela. Go and see it there. And I can kind of go to the pretty final slide here that in cryoscope, we then will use this, for example, for soil temperature. To understand how good is the bearing capacity of winter terrain, there are two factors. It's soil temperature or snow water equivalent. These are important for the forestry sector when they want to do fellings. And for this, we need new data sets, so more in situ observations for the soil temperature, for example, and then we have new cool products for snow water equivalent from a company called Snowcap that we can then train with new data. And then I forgot to bring this kind of in situ observation tool that we also bought there, that there's a forestry student who will make observations, but then a lot of nature guides as well in Lapland, so that we can get more fine-grained observations points in Finland. Yeah, but that's it. Thank you for your attention. I want to highlight that if you are interested in this reanalysis data, for example, we tomorrow afternoon have a user engagement workshop for this Copernicus Climate Change Service, where all the data comes from. And I think it's a really key asset that the Earth observation community would be a little bit more looking into reanalysis material as well. And otherwise, thanks to Oceanics, Aurora, Cryoscope. But register to that event. Thank you.
Thank you, Mikko. Any questions from the audience?
Hi, and thank you for a nice presentation. I was interested in the model selection, that while you are doing predictions in the future, and most of tree-based models and also XGBoost, like you said, they aren't really capable of extrapolation, so they will fail in these situations if you meet this sort of extreme values that were not in the training set. So are there some specific reasons then why this XGBoost was still seen as a best model to select for this specific purpose?
Very good question. We are not going forward in time with the XGBoost. We are only downscaling what weather forecast models gives us. So we are trying to just kind of downscale, in a way, information to this Earth observation product resolution from Earth system model resolutions. And that means that when we are in the future, our future steps come from the weather forecast model. They don't come from the kind of like us in the machine learning model for forwarding time. That's why we don't get that problem in the same way. But as I said, that if you want to get real extremes caught, then it's better that you have a long time series in the back, that there are significant. But we do actually have models that go outside of the training set extremes. It's just like, don't confine it by minimum and maximum. Use the mean, and how that changes is a better feature from the climatology of past observations than the extremes. Then we have examples that it works also for extremes. But I think a key point is here that we don't try to really do time series prediction. By machine learning, that we leave to the weather forecast model, which in our case can also be an AI weather forecast model. Doesn't matter. But we don't try to really go forward in time.
Thank you.
Thanks, Mikko. Let's give a big hand to Mikko also. Next up, we have Sonja Koivisto from CGI Finland.
Thanks. I'm going to present a really similar subject as Mikko, but from a different context of agricultural fields. I'm going to talk about the importance of in situ observations in building and developing machine learning models, and the context is agricultural fields. So first, a little bit of background about satellite monitoring. Then, what type of in-situ data do we collect, and how do we utilize it in the machine learning models? And the model is predicting the parcel status. And lastly, I'm going to present the conclusions we arrived to. So the motivation for this experiment was that we now have these 3 years of in-situ data, and we wanted to see how each additional year of in-situ data improves our model performance, and whether we should continue the data collection into the future. So the Common Agricultural Policy of the EU mandates every member state, including Finland, to monitor the agricultural fields by using satellite data, and this is to ensure the correct payment of the agricultural subsidies, and also to encourage environmental farming practices. In Finland, CGI has developed this monitoring system for the Finnish Food Authority. The monitoring process goes as follows. So as input data, we use Sentinel-1 radar data and Sentinel-2 optical data. And to those, we apply some image pre-processing to Sentinel-2, like cloud masks and then index calculation. And from the rasters, we extract the signal from inside the field parcel geometries, and then get, for example, a median of NDVI for parcel for a certain time point. And then we can construct a time series of those. And then we apply interpolation and smoothing and some further signal processing to those time series for the parcel. These time series work as inputs together with the ground truth data so that we can train the model. And we also use extreme gradient boosting, as in the previous presentation. And after multiple iterations of the model training, we can then pick the best performing model with the SHAP scores. And when we're satisfied with the model, we can then use that model to run the inference for all parcels in Finland to predict the status. Based on our analysis results, the eligibility for the farming subsidies gets evaluated, and if there seems that something is off with the parcel, then an evidence request is sent out to the farmer, and the farmer has a chance to reply with a photo, and then we analyze the photo with image analysis. And we hope that in the future, this system would also benefit the farmers and give some useful insights from our analysis. The in-situ data is kind of a cornerstone for our analysis because it's used in the model training process. And now we do have this 3-year time series of similar type of in-situ data with the parcel statuses. The data collection program is called In-situ for monitoring, ISMO, among friends. And it comprises of 20 different data collection routes located all around Finland, so we get a very nice geographical coverage, and these parcels are meant to represent all parcels in Finland very well. We change these 20 routes every year and also the parcels along them, and these routes are collected every week, so we do not miss any of the events happening in the parcel, because sometimes the parcel status can change quite quickly if you miss a couple of weeks during the summertime. And across 3 years, we have collected more than 5,000 of these parcel status time series. Examples of what the state of the parcel can be are growing, mowed, light tillage, plowed, whatever has happened there, or even if the vegetation is withered or the cereal has ripened. And we do the collection with a QField app. The temporal resolution is quite good, so we try to get a data point every week. Here is a real-world example of what a barley parcel from last year looked like. This was from close to Seinäjoki. So this is very typical. that first nothing has been growing there, it's just been stubble. Then in June, the parcel has been plowed before the barley was sown, and after that it started growing. And in mid-August, the barley ripened, and mid-September there was harvesting. And after harvesting, the cycle would be ready to continue again next year, maybe with a different crop for crop rotation purposes. And when we have very many of those type of time series for the ground truth data, we're then ready to train the model by using all those. Of course, we also need the signals to train the model with. So we use backscatter from Sentinel-1 and then 12-day coherence. And for this year, we're planning to add also the 6-day coherence, since there are now enough Sentinel-1 satellites available for that. From Sentinel-2, we calculate different indices, like bare soil indices, tillage index, different vegetation indices, and some concerning the crop residue. And on top of these indices and signals, we also have some other features for the model, like the crop type and the days since season starts, and these are actually also very important for the model. The model type is extreme gradient boosting, and then we have a one versus rest classifier on top of that. Here you can see how the different input indices from Sentinel-2 react to the different events happening at the parcel. So for example, if you look at the vegetation indices, they predictably drop during the plowing and sowing events, and then they reach their highest point in the middle of the growing season and starts a steady decline when the barley has ripened. And here is an inference output from our production model from last year, which can be then simplified to this so that you can see that it very nicely overlays with our ground truth data. So this model has never seen the 2025 data. It's been trained with 2023 and 2024. But still, the temporal accuracy is very nice. It's not always so neat, but in this case it was. And as to how much the model improves, for each added year, we did an experiment where we trained a model with 1 year, 2 year, and 3 years of data, and evaluated it against the same test set, which always comprised of 3 years of data. And the results were quite as we expected. Of course, the 3-year model should perform the best because it has the most data points, it has seen more of different types of parcels, and also the weather conditions which affect the crop growth, they vary with each growing season, so the precipitation and temperature and so on. But the differences between the models were quite small. As you can see, measured with these macrometrics, the recall increased a bit more than the precision. And you can also break it down to how well we were able to predict each status. So for example, from light tillage, we have the least data point of all of these statuses. So that's why we were not able to predict that so well. And on top of that, it looks very similar as to plowing in the field, so those can be easily confused. But for example, from growing, we have very many data points, so it's easier to predict. To conclude, even though the increases in the overall metrics weren't as big with each added year, the impact in our result is quite remarkable, because when we compare the 1-year model to the 3-year model, with the 3-year model, we get over 40% fewer undetected mowings, and this leads to very many fewer evidence requests, unnecessary evidence requests sent out to the farmers. So that saves the farmer time when they don't need to be replying to unnecessary evidence requests. The F1 score and the other metrics, they improved more when adding or going from 1 year to 2 years, and then a little bit less when adding the 3rd year to the data. And it's also good to keep in mind when adding new data sources to the model that you need a temporal overlap with the in-situ observations if you're planning to use them for training, as we now have the 6-day coherence for next year. Thank you. I'm really happy to hear if you have any questions, and here is part of our amazing team with their spacesuits on.
Thank you, Sonia. Any questions? Let's wait, you will get a mic.
The machine learning technique you used is extreme gradient boosted trees, right?
Yes.
So do you like to experiment with neural nets or something like that? Neural networks or convolutional neural nets?
We have tried different models, but this was the one that worked the best. And then we also do different analysis, not only this partial status prediction. For those we use, for example, the crop prediction. That's based on more of a time series model. So, but this partial status prediction, it needs to run continually during the growing season. So it cannot be any fixed type of time series, or the fixed length time series.
And one more, I feel like your model favors false positive more than false negatives, because if you have a false negative, then you need to request evidence, if I'm right.
Yes.
So can you comment on that? How do you balance that?
So as you can see, the precision still, we try to optimize the model so that the precision stays on a good level. And also, when we get the inference output, we run like separate traffic light system on top of that, and the subsidies are then evaluated against those traffic lights. So there is one layer on top of the model output, and then we can easily also optimize those parameters for the traffic lights.
Thank you.
Any other questions? All right, thank you, Sonia. There was one.
Oh.
Was there? Okay, thank you, Sonia. Next up, we have Kevin Bovary from Airbus presenting.
All right, thank you. So I know that you are waiting for Leah, but unfortunately she was not able to make it, so I will replace her. So she's my colleague. Nice to meet you. I'm Kevin Bovary. I'm in charge of our portfolio for geospatial solutions at Airbus Defence and Space. And today I will talk about how AI, and especially generative AI, are revolutionizing the geospatial industry, and especially geospatial intelligence, globally and also at Airbus Defence and Space. Is it working? No. So we just need to solve a minor technical issue. Okay, right. Right. First of all, I wanted to introduce you the different waves of AI. So, of course, you are all familiar, and there were already presentations about the first wave, which is around deep neural networks, which are using a large amount of labeled data. So we have been using deep neural networks for years already in the industry, and especially at Airbus. We have been building detectors and classifiers typically to detect and classify aircrafts, vessels, vehicles, and a lot of other things, also buildings, for instance. But the real transformation and the real revolution happened back in 2017 with the introduction of transformers by Google, and this is when we started to talk about foundation models, which are basically pre-trained models on a large amount of unlabeled data. And this is what we are currently using, and I will deep dive into that after, to develop multiple tools with limited fine-tuning. And this is how we can aim, for instance, for automated analysis reports, for instance. The last wave, the third wave, is also one that we are entering. It's the general AI wave, which is also quite a lot about agents. You probably heard about agentic AI. So the idea is not just to react as we are doing today, but to be able to reason, to plan proactively, and to act. And also the concept is very much to connect with multiple software and tools. And a good idea that something that we are already exploring is how to autonomously orchestrate satellite operations to monitor specific area and do what we call tip and queue. So okay, what are the challenges on the geospatial intelligence side which are driving this need of AI? So actually there are three of them. The first one is around the amount of data that we have to process. So probably know all of you that there are more and more satellites in orbit, more and more Earth observation capabilities, a lot of different sensors, a lot of different types of data. And it has become actually difficult to leverage all these data capabilities. So that's the first challenge. The second part is it's quite difficult to predict any kind of situations and to develop an ad hoc solution, and especially AI models which are able to react to any unexpected situation and also customer demand. And the third thing is the need also to democratize the access of such data. Of course, it has been reserved to a lot of specialists of Earth observation imagery or geophysicists. But the question is, okay, how can we open and democratize the access to this data, not only in the defense domain, but also in a lot of different applications. And for all these different points, actually, AI and general AI are providing a lot of answers. If we look at it now from a different angle, look at, so this is a representation of the value chain on the Earth observation side. Actually, we see that already AI is impacting the entire value chain. So it starts from the operations, where we can have AI systems to help automate the operations. I mentioned it earlier. It goes then to the imagery product themselves. And I will show you actually what we are doing at Airbus, for instance, to improve the resolution of the satellite imagery. It can be used also for imagery processing, to filter, for instance, remove clouds from images, or haze and other artifacts that we don't want to have when we analyze images. And then we go into the application part, so the end of the value chain. Of course, this is where there are the most applications for image intelligence, for mapping, to be able to detect, classify, and identify different objects. And I mentioned it also earlier, but we are more and more now seeing generative AI bringing new capabilities to automatically generate reports. And then ideally, if we imagine a bit the future, have actual co-pilots or assistants working together with analysts, so they can basically help them to develop any solutions very quickly and don't have to develop a lot of software. Actually, you can ask questions, and the agents and the models will actually do everything for you. So that's the first example I wanted to show you today. So this is something that we are doing at Airbus for a few years now, and it's a very good usage of AI. So we have our amazing satellites Pleiades Neo, providing 30 centimeter native resolution imagery. But we wanted actually to do better, and we use AI to improve the resolution of these images and to provide 15 centimeter aerial grade imagery. So actually, the models were trained based on aerial images, and we are providing very reliable products at 50 centimeter, which are actually keeping all the properties of our 30 centimeter products. So it's obviously an amazing capability, and you have seen that probably many operators are going this way. The good thing is that we are opening new kind of use cases that were never possible in the past with satellite imagery, at least commercial grade imagery, especially on the utilities, infrastructure management, and of course defense as well. Now I want to talk about more on the applications, and I will focus about defense today. So there are two main areas where we are using AI at Airbus, and one is image intelligence, IMINT, and the other one is defense mapping, so cartography. So we use AI all along the value chain, as we have seen before, but especially for image intelligence, we are using AI models to detect, classify, and identify, as I told you before, and now we are starting to use that to generate reports. The idea is really to mimic what a human analyst will do. So basically, the same way you will train a human being to analyze what is on an image, the idea is to mimic that, but with a foundation model that is able not only to detect and classify things, but actually interpret the results and provide to you a comprehensive report with contextual data. So that's where we are aiming to. On the mapping side, it's also very much about automation. So we have been using AI for a while to detect the geometries of all the objects that we want to map. So basically, you can detect building footprints, you can detect roads. Now we are able to also detect walls, edges, and a lot of different elements. And more, all the geometries will be detected automatically. Of course, there is still a big work to do on the attribute extraction. So for each object that you are detecting, you need to qualify and to explain what are the parameters associated with this object. But the aim is to progressively automate all that, and the end goal actually is to move from maps which are built and which are taking like weeks to be built to days and maybe to hours. So yeah, that's the intention. All right, so I will accelerate a bit. So generative AI, I mentioned it several times. We are using it for three different things. First one is to speed up the analytics development. So I mentioned the analytics. It's not exclusive. It's not because we did in the past deep neural network that will stop. Actually, the idea is to combine everything and to have generative AI helping us to interpret the results of such analytics. The second step is speak and interact with an image. And I have a small video I will show you right after. But it's really to be able to interact with the image and ask questions to the system. Can you find me this very complex pattern? Can you find me a vehicle there? And really interact like with a chatbot and discuss and explain the situation that you are looking for. And in the future, as I said, it's to be able to handle very complex use cases, fully autonomous, fully predictive solutions, like tip and queuing, orchestrating the full satellite system. So that's the final slide. So I wanted to introduce to you Airbus GeoExplore, which is our new tool. It's still on development, so it's for now relatively new. I said that at the beginning, one of the challenges is to handle a lot of data. So actually, this tool is the answer to that. Is a way for analysts to quickly search for something in a very large database. So it's a wonderful companion for analysts. It can quickly help to find objects, detect patterns, or even situations, and describe them textually, and then ask to the solution to fetch all the results he finds in the imagery. It's also a good way to train very quickly AI models. You can create label data very quickly. So I don't know if we can run the video. So that's basically, maybe you can go in full screen. I don't know if it works. just a first simple demo, but so you will have a prompt, and the same way you are interacting with ChatGPT, Gemini, you'll be able to ask for any questions, find this object in this area, find this object close this kind of building, etc. Even more complex questions, and the system will give you all the results it's finding. So it's a bit like a Google search, but in satellite imagery, and we can deploy that not only on our own imagery, but any kind of imagery, and even maybe other data. So sorry, the video was very quick, very short, and small screen, but I think you understand the logic. I will be there for the day, so feel free to come by, and happy to discuss with you if you have any questions. Thank you.
Thank you, Kevin. A very impressive presentation. Any questions? Yeah, you have done a lot. A very impressive presentation. How do you see that? What are the current constraints for? Are there like computational constraints, or I would guess that like a global system like this that you're describing with this global AI system would be very computationally intensive. How do you plan to solve these kind of problems?
Yeah. For now, the biggest problem we have is to make sure that it's working. It's not so obvious, actually. I mentioned some of the use cases, so we are still experimenting and seeing what the models are able to do. We are working also with a lot of partners, companies in Europe and also in the US. That's the second challenge, the need of having very strong AI companies in Europe, so we don't depend from US companies on that side. But we do have good partners, especially in France. We have Mistral AI, for instance. So that's about that, like building the proper visual language models, so models interacting with both imagery and text. Then computational power for now is not really a problem. Of course, if we look at evolutions and maybe at some point having edge processing, so directly on the satellites to speed up even more the process, or directly deploy capabilities on a battlefield, that could become a problem. And so we are also looking at miniaturization of some of the models, or being able to run these models with very small capabilities. But we are not yet there. We are exploring things in parallel. The first thing is to make sure that it's working and delivering what we're expecting.
Thanks, Kevin. Let's give a big hand to Kevin also. And we will conclude this session with a keynote from the European Space Agency. Let's welcome to the stage Lauren Jaffard.
So very good morning. My name is Laurent Jaffard, the Director for Telecommunications at the European Space Agency, and I would like to give you a bit of an overview of what we're doing post-Ministerial 25. In particular, what are the opportunities in Finland and in the Nordics. So you know that we had a very successful ministerial. We collected 22.3 billion euros across the 23 member states. My directorate represents a little bit less than 10% of the overall amount. We managed to get roughly 2.1 billion euros for connectivity. It is absolutely important that we work together now with industry to spend this money. So it's up for you to grab it. We have, in my directorate, 3 domains. The first one, which is the legacy, ARTES 4.0, where we're building partnership with industry, where we are looking at development of technologies, where we're looking at helping industry, helping academia, work on topics that you would not necessarily finance entirely by yourself. And we're coming with a partnership approach with a co-funding model. We have another program called Moonlight, where we're looking at connectivity and navigation to the moon. This is really to enable the exploitation of the moon. It is to enable astronauts to go back to the moon. And we are hopefully giving the infrastructure for lunar economy to blossom. We also have the ESA program for the related EU secure connectivity, the so-called program RY2, and I'll come back to it in a minute. So roughly 1.5 billion for ARTES 4.0, 176 million for Moonlight, 383 million for secure connectivity, and a little bit of a legacy of ARTES before ARTES 4.0 on exploitation of data coming from satellites that have been already launched. We had a very strong support from the member states. There is a strong underlying importance for innovation. Europe in telecommunication has, in some areas, gaps. In some areas, we are leaders, and we need to level up where we have gaps and maintain the leadership where we are very strong, in particular when it comes to optical and quantum communication. We also see a strong need to improve and work on the topic of resilience. Resilience is another word for defense. We need to make sure that we preserve the sovereignty of Europe, that we preserve the autonomy of Europe. And the developments that we are taking are there to help Europe be independent and not rely on third-party states that may at one point in time cut the supply. So industry has a key role for the implementation, and we are here to support your competitiveness globally. When I go now to the RY2 program, we had 3 elements of this program. The element 1, which is really to improve resilience, is to work on the supply chain, is to work on the Europeanization of solutions that may not be in Europe today. The element 2 was not subscribed because it is for later. It's all about applications, and the applications will come once we have deployed the infrastructure. And the element 3 was broken down into 3 areas. The first one is to support the user adoption. This is really working on user terminals, key building blocks of those user terminals, looking at cheap and terminals that can be produced in large quantities. Second element was around the low LEO expansion. RY2 is a multi-orbit system, MEO, LEO, and we're now introducing the 3rd layer in low LEO. The 3rd layer is to work on what we call pre-operational services, new services that will be benefiting the backbone of communication, that will basically shorten the time between tasking and dissemination of data. And then finally, we're looking at the evolution of RY2. RY2 has been defined roughly 3 years ago. It took a lot of time to get to a concession contract, which was signed in December 24. And now we are already looking at how can we enhance this system. So we're going to have a very strong partnership with the European Commission. It's a joint program. We will work with the European Commission on this low LEO expansion. We'll be looking at 2 aspects. One, which is a sandbox. That means demonstration of capabilities in isolation. And then the second one, which is pre-operational, meaning demonstration of capability in an operational context, and to basically have an intermediate steps before we have a full operational service. ESA will lead this low LEO expansion. We will have the design authority for this low LEO expansion, and we will work with the consortium of operators called SpaceRise as they are handling the concession. We are also looking at a polar option to bring low latency polar coverage. And here again, this is of high importance in the Nordic countries, but this is an aspect of resilience on top of the other layers. So now that we got 383 million, we're going to be issuing an ITT in the first semester of this year. The target is to reach a PDR in 28 for the expansion of the system. We are looking at the low LEO with pre-operational services in 28 before the ministerial. And as we are currently entering into a key milestone of the program called Rendezvous 1, right after the Rendezvous 1, we'll work on the resilience of the supply chain. So stay tuned. There's going to be a lot of activities coming up. I wanted to show an illustration of what would be this evolution of the system. We are going to move from a pure secure communication constellation to a governmental transport layer backbone that would provide the capability for other space domains to connect into such a backbone. We are trying to look at the sensor to shooter loop and how to reduce this lead time before you get information and you're able to act on this information. So this is not just about dissemination, it's also about the tasking and what we call the command relay. All of it is prescribed into a program which we called European Resilience from Space, and where we're going to work on an integrated system of systems. We're going to have 3 pillars. The first pillar on Earth observation, and my colleague Dominique Géron is unfortunately giving a parallel keynote, so you'll have to ask your colleagues. The PNT, it's very key to have a much more resilient signal of PNT. You're experiencing with the neighbor on the east a lot of jamming. We need to have a much stronger signal. We need to be able to combine these accurate positioning with the imagery and the telecommunication part. When I go to now the ARTES 4.0, we in fact received 125% of what we asked for. This means that the member states oversubscribed the program. We have a lot of topics. We are organized into what we call industrial competitiveness, the core and the bulk of our activities, which are generic to be used by the different areas of the telecom industry. And then we have 3 strategic program lines. The first one on 5 and 6G, the second one on optical and quantum communication, and the third one on what we call 4S, which is Space System for Safety and Security. And here we're looking at topics like security by design, cybersecurity, maritime and aviation. When we look at those activities, these are activities which are co-funded. And we have worked a lot with the member states to simplify the way we contract with industry. We have this principle of co-funding. We have for LSI, lead system integrators, a increased level of co-funding up to 75% until TRL6, and then 50% post-TRL6. And then we have for SMEs up to 80% of funding throughout the whole cycle, and for academia, 100% to participate in consortiums. So what we want is to have clear roadmaps on how those technologies are inserted into products, that are inserted in subsystems, that are inserted in systems, that are finally making it to a mission. We are not interested in technology for the sake of technology. The demand from our member states, the demands from the users is to have capabilities ready for use. Now, let's zoom into the 5G, 6G area. We have worked a lot on the direct-to-device concept. In fact, we have 2 partnership projects with leading operators that I'll introduce later. We also have created hubs And we would like to have an in-orbit laboratory where we're going to be able to test 6G, where we're going to be able to help industry prepare for the unification of terrestrial and non-terrestrial network. Of course, we need to bring in AI in networks, not a trivial topic. We're going to be reaching into new domains, automotive. We are going to be looking at forums discussion. There is the upcoming Mobile World Congress in Barcelona. You're going to see a lot of satellites. In the last 3 years, progressively, satellites were starting to appear in that show. And that shows the interest of the terrestrial network and in particular cell phones to be connected anywhere, anytime. We are working on 5G Emerge. This is a project which is in its second phase. We'll be looking at the third phase next year. And here we are looking at broadcast and multicast. So close to home, direct to device as well. Now looking at direct to device in more details, we have 2 partnership projects that we're starting. The first one with SES, where we're going to be developing and validating this 5G non-terrestrial network connectivity. We are looking at a concept where SES would relay the network through its MEO constellation. And we're going to be looking at Viasat with a time to market for Viasat of 2028 for the first generation. And we are looking at inserting European technologies in this global constellation. And behind Viasat, you also have Space 42 in the Middle East. For 5G Emerge, I mentioned it earlier, we are setting up the phase 3. There's a lot of Nordic state industrial contribution currently, and we believe that this program is helping de-risk technology, demonstrate technologies, so that we can insert those capabilities in the overall unification of the different networks. So that concludes my presentation, and I'm open for any questions either here or later during the day. Thank you.
Thank you, Lauren. Very impressive presentation again. Any questions from the audience?
Thank you for the presentation. One important aspect for secure communication is encryption and cybersecurity. What are the capabilities you look for, at least in Iris Square program, for the encryption and like reliability of the secure communications?
It's a classified answer.
Thank you. That was really concise answer.
Other questions? I think there are a lot of like small companies here at the Winter Satellite Workshop and small and medium-sized companies in the private sector. What would you like to say to them if they want to like move forward with the like collaboration with the European Space Agency and these topics that you mentioned?
Thank you. We are very interested in the entire ecosystem. We are not solely interested in the lead system integrators. In fact, in our programs, we have set a certain threshold for the consortiums to embark SMEs and startups. For Iris Square, 30% of the program is dedicated to SMEs and startups. So I strongly encourage you to contact us on the low LEO part. There are great opportunities for SMEs and startups to demonstrate, to potentially bring pre-operational services. On the large constellation, there are also opportunities. There, I would direct you to SpaceRise. So this means SCS, Eutelsat, and Hispasat. We have other programs where we are supporting SMEs. You have up to 80% co-funding from the agency. This is really a chance for you to de-risk the technologies and help yourself grow. We are interested in your ideas. Please contact your delegate. We are working with the concept of letters of support. So the delegation will approve your application and will be able to proceed. I would like to also say a word on academia. A lot of the innovation, in particular for the lowest TRL, is happening in labs, and we are able to support academic research, but in a consortium. So you need to come up with SMEs and larger companies, and for academia, we're able to finance up to 100% of your work.
Okay, thank you, Lauren.
Thank you.
Let's give a big hand to him. That concludes this artificial intelligence for Earth observation session. We will have a coffee break now, and we will continue in this room at 10:45 with the fireside chat.
And liftoff of
check, check, check. Check, 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 check. 안녕하세요. Okay.
Hello, hello, hello. So welcome to the hall. And next we're going to have one of the few fireside chats we have in this event. And we are going to dive deep into the really futuristic topics, future of space, quantum, maybe a little bit of AI is coming as well. And we're going to have on the floor 3 specialists, and the whole fireside chat session is going to be hosted by Pauliina Rajala. And Pauliina is introducing all the other speakers as well. So Pauliina, come to the floor and let's get started.
Thank you, Jan. It's my pleasure to be here today, getting wired here. So we're beginning with Professor Jukka Pekola from Aalto University, and Jukka is the director of Institute Q, the National Quantum Institute. And Jukka will give us a short overview of quantum technologies in Finland and how we are organized here. After that, we move to the table with myself and Tommi Tenkanen and Jukka and explore a little bit about the quantum technologies, what they look like today, where Finland stands with quantum technologies, and what overlapping areas and interesting aspects we have when we look through the lens of space to quantum technologies. So welcome, Jukka.
Yeah, thank you, Pauliina, and welcome everybody. As Pauliina told, I will present the Quantum Institute, the National Quantum Institute here, and a little bit of the research profile that we have on quantum in Finland. So, Institute Q was actually, it was founded a few years ago, 2021, and it was essentially founded on top of the Center of Excellence in Quantum Technology that we had been running since 2018 here in Finland, coordinated by Aalto University, but we had other partners at that time already. We had VTT, the state, and then University of Helsinki. So it was really a capital-centered institute from the beginning. And the goal from the beginning was really to raise the readiness of Finnish society for this new, let's say, new technology which has potential and implications for society and economy in the future. We have, as I will show, we have quite a lot of expertise here in the country and long-term activities in the quantum science and quantum technology as well. So it was a very kind of a good starting point for such an activity. But what happened now in, let's say, last year, in fact, in August 25, we expanded this institute to cover the whole country. So all the important, let's say, essentially all the higher education, let's say, universities and research institutes that are doing quantum technology in the country. So besides Aalto University, University of Helsinki and VTT, we now have 7 other universities and then, or 7 universities and then CSC and VTT as research institutes here. CSC is the IT Center of Science. So this also reflects the fact that quantum, although you may consider it quantum technology as hardware-driven research area and technology area, it also is, of course, in an expanding way. It's going to be also covering a lot of IT software algorithms. So this is the status now. we have all these institutes. We are actively have started this activity together, and the whole institute is centered around 3 different pillars. There's a kind of a task force, or let's say all these participation organizations are involved in all of these different pillars, and one of them is naturally the research direction, so RESCUE as we call it, which has this fundamental applied research and infrastructure development in Finland to really support the quantum tech research and quantum science research as well. So I personally am more on the side of quantum science rather than technology, but of course with a view to the technology as such. But very important for the Institute is that we have also this educational direction, EduQ, which is developing let's say the workforce and the talent and really the resources human resources for the rising technology area. And this is a direction that is currently led by University of Helsinki. I forgot to say RESCUE is led by Aalto at the moment and EduQ by University of Helsinki. And we had a kind of a boost in this direction last year when Tommi Tenkanen, one of the panelists here, did kind of a survey about the needs, and we will hear more about that probably in the discussion today. And then we have the InnoQ, which is a very important direction because it's not only, of course, not only research. We also need to have the ecosystem development and connection to the society and connection to the companies beyond these public institutions. So we will probably in the discussion touch many areas of quantum technology, but I will tell kind of my personal view because I have been involved in this research already that long time that I know the history very well and why we in Finland do quantum research and technology. So we tell here that Finland is kind of a forerunner in this direction because Finland had already in the 1960s a very strong activity in what was not called quantum technology at the time, but in the areas which have now become the core of quantum technology, namely the solid state realizations of quantum technology are really based on a lot, at least here in Finland, on what we did already many decades ago. So there was a low temperature laboratory led by academician Lounasmaa, which was founded in 1960s, and it developed already at that time cryogenic technologies, which are now the enabling technology for quantum tech with many applications. So from that we have generated industry, for instance, this Bluefors, which is the market leader in providing the low temperatures for quantum devices and quantum computers that are now built. But over the years, the research from doing this very low temperature research, which needed these low temperatures, was moving to different directions. Initially, it was about superconductivity and superfluidity, but over the years, it also transformed more to the nanoelectronics and superconducting circuits. But in the meantime, there was a lot of development about squids. Squids do not mean squids that are in the water, but they are this, many of you of course know. So they are the superconducting sensors, or let's say superconducting junctions, which were used already in the 1970s and 80s for imaging the human brain and also heart. So this technology was developed at that time in this same environment, and it really serves as the prerequisite of modern quantum qubits, the quantum bits that are used. So as I mentioned, I really give a little bit of a biased picture here, but I would say that in Finland we have different directions that are being pushed forward. One is, of course, quantum computing. We have very large projects. We have a big company, IQM, working on hardware of quantum computing. We have companies also in the software and algorithm side. So this quantum computing as such is, of course, the most visible part of the quantum tech. But there are other areas of quantum tech as well. For instance, quantum sensing, which is of course, very close to you people here, because sensing is in your context is, of course, an important aspect. But we are quite well in that direction as well. It's a growing area, and especially using the superconducting circuits, it's quite a promising area of research. So my own research is quantum thermodynamics, which is actually also very closely related to sensing. So we are developing technologies by which we can thermally sense the quantum dynamics. For instance, here you can see on the left, we have a superconducting quantum system whose dynamics can be monitored by simply making a very sensitive bolometric detector of heat, the energy that the system is expelling under the driven conditions. And this is kind of a new way of looking at quantum dynamics, and it can actually give information which is not obtained and in different regimes which cannot be obtained by conventional means. Also, talking about sensing, these superconducting qubits and qubits in general, are not only good for computing, but they are also good for sensing. For example, in my research, we use superconducting qubits as thermometers of the surroundings. So in general, I could say that quantum technology is one of the ways to really make really sensitive observations, sensitive measurements down to the level that is not usually obtained by other means. But putting the research aside, I'll just mention here two different documents or two different achievements on policy level. So one is that in last year, in April, the Finnish this Ministry of Economic Affairs and Employment published the quantum technology strategy, which was developed among the different stakeholders working in quantum tech, ministries, researchers, companies, and so forth. So this is very important for us because now Institute Q plays a critical role in the execution of this quantum strategy. So especially we are in charge of doing this national coordination of research and education, the competence center, and we have to take care about the infrastructure development in the country in this direction, and also the innovation and international cooperation aspects. So Institute Q plays a big role in this strategy, which is now made for next 10 years, or let's say till 2035. Another important thing is this Finnish quantum technology roadmap. I just flash it here. I think Pauliina will probably tell more about this in the discussion. So there's this Finnish quantum strategy roadmap, which was just recently started. The three focus areas of this roadmap are the quantum computing, communication, and sensing. It's a living framework that evolves through this community engagement. And there's this launching, how do you call this? There will be this event on 27th. There's a webinar on 27th of January, and you can see here this code for it. So then we will go to the discussion part, and I think Pauliina was already introduced here. but I introduce her once more. So Pauliina Rajala is the development manager of Institute Q here, working really, she's a shared resource for whole Institute Q, and she has started this activity last year. And then the other panelist is Tommi Tenkanen, both of them PhDs, naturally. And Tommi Tenkanen is now hired to VTT to start to set up this InnoQ activities from the beginning of this year. Otherwise, you know him for sure as an author, writer, and a consultant, and a physicist. So I think with these words we can probably go to the discussion. Thank you.
Thank you, Jukka. And if you don't mind, please join us in the discussion. So when Johan and Jan approached us to participate in this magnificent event, and the thinking behind was that there's a lot of disruptive technologies, novel technologies.
What is that?
Yeah. So, and technologies that are talked about a lot, and technologies that we assume will play quite crucial role on other technologies. The previous session we had on AI, and that is one of the disruptive technologies that is quite mature already, and we heard a lot about the examples how AI is currently being used in a space and satellite and remote sensing. And quantum is another technology that is categorized as disruptive technology that is developing currently really rapidly and has a lot of promises. And technology that will interfere with other fields very deeply if our vision is valid. So that's why we are talking about quantum today in a perspective of space. And first, I think not everybody is as thoroughly read in quantum as we who talk about quantum every day. So would you, Tommi and Jukka, would you summarize shortly about like how we categorize quantum in three areas and what they mean in a very general way?
Yeah, thank you, Pauliina. Maybe I could start by indeed reminding everyone of the three areas that Jukka presented in his talk some 5 minutes ago. Quantum technologies are usually divided into three areas: quantum computing, quantum communications, and quantum sensing. Nature, at its core, is quantum mechanical. Quantum physics is really the most fundamental theory of nature that we have, and thus, when everything is built on quantum physics, one could say that all phenomena are quantum phenomena. Quantum physics is at the core and at the heart of everything. But really what one means by quantum technologies is not just the fact that the physics is based on quantum mechanics, quantum physics, but it utilizes quantum phenomena by controlling them very precisely, whether it was in quantum computing, sensing, or communications. Lasers, for instance, they are traditional technology that at the heart are quantum mechanical, but that doesn't make them quantum technology unless you are controlling quantum phenomena such as superposition and entanglement very precisely. Maybe Jukka, if you want to amend this.
At large, actually, it is exactly as Tommi was explaining. We have seen quantum mechanics now in action already for a century or so. but over the years there have been new technological developments thanks to quantum already. So we have had transistors already like more than half a century now, and then more recently we have seen this development towards quantum devices in solid state, like this superconducting ion, different realizations of qubits, the quantum bits, which give a lot of opportunities to make devices. We mentioned computing, simulation, but also the sensing is a very important aspect that can be done. And as technology also, we really should not forget the importance of the software side, soft side, because at the same time as we put a lot of effort on developing hardware, the time will come when also using this information that we get from these devices is to be processed.
Thank you. And there's a lot of political activities around quantum currently. So EU launched the EU quantum strategy this summer. Finland launched the Finnish quantum strategy in April last year. And a lot of these strategies actually look at space as well. So quantum and space is there usually mentioned, and interestingly, it's a double, that space and dual use. So this kind of like gives us a hint a little bit how, in the political context, the quantum and the space is used. So it links to cybersecurity, it links to safe communication and remote sensing in kind of like challenging conditions. Mm. But there is a lot of promises in peaceful use for quantum as well. But I find it quite curious that it's actually one of the fields of technologies that is not quantum. The space is mentioned in the titles of these strategies. And would you like to give us some of examples, for example, from quantum computing, where we have interactions to satellite and space and remote sensing side?
Yeah, absolutely. Quantum computing is a new type of, new way of doing computation, because you are not, when you are doing quantum computation, you are not using classical physics, classical information processing, but indeed quantum information theory and quantum information processing to enable calculations that you wouldn't otherwise be able to perform. And due to this enhanced computability or computational processing power, one can use quantum computers to solve, for instance, fluid dynamics equations, something that is very important for aircrafts and space shuttles that improve their operational capacity. Another area that one could use quantum computing for is image processing, something that is relevant for remote sensing and telecom. Also, perhaps on a more futuristic side of quantum computation, at some point we will probably have quantum internet that is enabled by satellite links connecting to remote or multiple remote quantum computers at different sides of the Earth together.
Yeah, so I see this a little bit, not differently, but a different aspect from this. So quantum tech is still a developing technology. My favorite example is this, that the qubits, which were in solid state, they were invented like just before the turn of the century, 26, 27 years ago. At that time, the lifetime, the time that you can do something with them was 1 nanosecond. Today it's 1 millisecond. So there has been a million times improvement in their capability to perform as quantum devices and for quantum computing. But still, today, this does not allow us to build a full-scale quantum computer, and it really, we still hear today that in order to have one logical qubit, you need 1,000 physical qubits in the system to correct the errors. So there's a lot of development in the direction of improving the fidelity of these devices, and as soon as this is in order, then one can think about computing applications also. And I don't want to say that this is something which stops thinking about the space applications of quantum computing at the moment, but there are also many low-hanging fruits, like in sensing, where you can, I just showed you from my own research that you can use qubits, even if they are not yet that high fidelity, you can use them for sensing, for instance. So that's probably closer to something that you people can think about how quantum tech can be used in your efforts.
Indeed, and if I take a step back, probably most of you know like what qubit is and how quantum computing works in principle in a like general level. But our old-fashioned computers, they use bits, binary factors, and qubit in other forms has ability of being something else as 1 and 0, being both and everything between. This is very dramatic. So that allows us, in theory, compute problems that are inherently quantum-based problems. So we can model very complex things because nature, as Tommy said, is inherently quantum environment. So that's the benefit. But as every light switch in this building is binary, but it does not make this building a computer because those light switches are not connected and controlled. Same, we can put thousands of qubits technically in the same device, but if we cannot control them, it's not quantum computer with that power. So that is the struggle where we are currently. Quantum computers, to my understanding, still, like at this moment, we have examples of use of quantum computers where we can see benefit of using them over the traditional high-performance computing. But it's still not what we like to call a quantum advantage, a step where we can do something completely new that was not possible with the high-performance computing in the traditional way. Do you want to reflect?
Yeah, that is indeed correct. Quantum computing is based on a very different technology, and because of that providing in the future new types of capabilities. But to make it work is going to be a challenge, and it will take at least another 5 to 10 years to see those major extra capabilities that are superb compared to traditional technologies.
And this is where we face the one challenge of the field, is because it's inherently different. The programming of these computers and the algorithms that we use to control the computers, but also the software we develop, needs to be different for us to take the advantage. And this is hard to develop when we are still developing the hardware at the same time. So we are like moving in two fronts. Also, we are seeking the use cases. What will be our first steps of?
Can I suggest that we turn these mics off and try the other mics?
Yeah. I think that was a little bit too dramatic for my flavor. So why I bring this up is that we... Thank you. Is it on? Yeah. So why I bring it up is that because we are facing a huge gap in the talent as well. So talent, of course, like in the hardware side, but growing need for talent in the software and algorithm development. And Tom, you did a quite impressive survey on that, an estimation of the numbers, what type of expertise we need in the future years.
Yeah, that's right.
How many PhDs you need to make
Yeah, indeed. Quantum technologies, when they mature from the present stage, will generate not only new types of solutions and revenue for companies that will develop those solutions, but also new jobs in Finland and elsewhere. Right now, in quantum technologies, or in quantum research and quantum technologies, we have roughly 1,500 people working in Finland. That's the number today. But assuming that quantum technologies, from sensing to communications to quantum computing hardware and software development, will keep developing at the pace that they have done thus far and maybe accelerating in the next decade a little bit as well, we will see most likely thousands of people working in this area in 10 years' time. According to the quantum technology strategy of Finland that was released last year, the target is that we may have at least 10,000 people working in these areas, sensing, communications, and quantum computing combined. If we take a more conservative approach, still what we saw in our forecasts last year was roughly 5,000 people working in this area. And that is a challenge for universities and research institutes, as well as the workforce and companies in general, because not everyone is an expert in quantum yet. But maybe in the near future, we will see more upskilling efforts. This is something that we are very much dedicating time and effort for, but something that is definitely needed in order to realize this.
Yes, so this is exactly the case, and I would say that we are quite well off at the moment in the education training of PhD level people. So the top part is in good order at the moment, and we even have this, as you have for sure heard about this 1,000 doctors program, which in quantum technology meant that we got 90 new PhD students in the area just a year ago in Finland. And these people are, of course, the ones who at the moment, there are PhDs who now lead these companies that are now mostly visible in quantum area. But as we just discussed, there are a lot of technical challenges, and this is not something that is solved only by PhD level people. I mean, the very mundane problems, like which you also know in detection in space science, is that you need a huge number of wiring to your system, and this is one of the limiting things at the moment for quantum technology as well. So we need really technological people, workforce, and also this is the same in both in hardware and in software.
Indeed, and in Institute Q, we obviously don't want to poach the experts on our colleague areas or other areas, but we are looking to combine our efforts of educating together the workforce, the future workforce, but also re-educating the experts already in the companies on the sufficient level that they have enough capabilities to understand what quantum is and what is the hype and what is the real promise and how it could be utilized in different business cases. If we take a step from quantum computing, which is a field of quantum that is mostly attracting attention, to the other fields of quantum, let's say the communication, because the quantum communication, that is something that we go to the space or the upper atmosphere and explore the possibilities there. So qubits and quantum phenomena is in a kind of like tricky and curious in that sense that if you measure it, you destroy it. And this is the secret for extremely safe communication. And Tommy, do you want to explain that further?
Yeah, quantum communication is another new type of technology. What you typically use it for is key distribution, because the laws of quantum mechanics enable one to generate random keys that are not repeatable and also that allow for communication that can't be eavesdropped. And that is definitely a big strength for communications. When you have a random one-time key that you use for communications, that is something that provides absolute security for distributing different types of messages. What enables that is indeed quantum mechanics. Typically one doesn't use quantum mechanics for the communication itself, but just for generating the random key that is only used for one time, and what that then enables is enhanced and in principle absolute security. So it's an exciting possibility for different types of use cases, whether talking about communications in more or less regular telecom, in finance, or in defense, for instance.
Yes, so this is an area which is not that advanced in Finland, I would say. So Finland is very active in quantum computing and sensing at the moment, but communication is perhaps a little bit less developed area.
Yes, we are a partner in the European consortiums there, and there's been pilots between Helsinki and Tallinn to establish these quantum links, and there's quite exciting preliminary results on that, but quantum communication is not fully there yet for us to utilize, but it's something to keep eye on. But if we keep our eyes on satellites, like we use satellites to distribute the quantum keys, but we actually use quantum technology as a really critical part of satellite technologies in the state-of-the-art satellites. And one of examples is atomic clocks that is relying on quantum technologies. What other equipment or let's say technologies there are that are utilizing the vast field of Earth Observatory, for example?
So what are the other? What did you want?
Do you want to expand that? Like how do we utilize quantum technologies in sensing or hardware of other technologies such as satellites?
Yeah, so quantum gives the possibility in sensing to use this quantum parallelism to really make the sensors much more sensitive or else much faster. And there are several examples of this, so that's already possible using the present day qubits already. So.
I think that's a great example of the technologies that we actually have a quantum technologies utilized all over us already, but it's called physics, it's not called quantum. And it's only very recent years when we started using word quantum technologies to describe all these technologies that actually rely on quantum. So this is part of, I wouldn't say like hype, but it's awareness and a new terminology that actually makes us a little bit forget that it's something that we've been using quite long already.
Partly, I would say, but there are new things as well, especially when it comes to quantum computing and quantum sensing using purely quantum phenomena, such as superposition that allows, for instance, particles to be in two different positions at the same time when they are in the true quantum superposition state, as well as entanglement, where you can control very distant particles or quantum devices in such a way that you can, in principle, or say effectively go past or beyond the speed of light in doing that.
Yeah.
So there are new things as well that haven't been produced or manufactured ever before.
Yeah, of course. And you mentioned some of the key things about quantum. Like one is the entanglement, and then there's a decoherence. And would you want to expand a little bit more for us to understand what it is actually?
Superposition is the thing that you, as already discussed, is enables the difference between classical computing and quantum computing, because having a superposition, you enhance the phase space, or let's say we call Hilbert space of the system enormously with a number of quantum objects that you have playing together. Entanglement refers to the fact that you have different quantum systems whose state is entangled, in a sense that as soon as you measure one of them, you know what is the outcome of the other partner, even if they are far distantly apart. And these are the key things that now, as Tommy mentioned, makes a difference in the current efforts to try to make use of quantum phenomena, as opposed to what was done earlier, which was also quantum in a sense. I talked a lot about these squids, for instance. They already obey that it's a quantum phenomenon, but it doesn't have any relation to these superposition states or the entanglement. So we often talk about quantum technology 2.0 now that we are searching for different opportunities to develop new sensing techniques, develop quantum computing, quantum simulation, just thanks and communication thanks to these properties that were not harnessed before.
And if you look deeper in the quantum sensing, I think the interesting areas or promises are for position, navigation, and timing, and providing GNSS independent navigation. So would you want to explain a little bit more about the opportunities and activities there?
Yeah, that's right. Quantum technologies, quantum sensors to be more precise, have been thought of replacing satellite-based positioning systems. However, even though they may be much more precise and something that work in denied environments, the drawback there, at least at the moment, is that what they provide you is not an exact location in any sense, but a reference position compared to grid points that you have determined prior to measuring your position. But it's an exciting opportunity still, because it gives you freedom to operate in spaces and in conditions where the satellite-based positioning systems may not work, or where you need some type of extra capability to position yourself, whether in space or in time.
And I think the challenge currently with these technologies is like they are working quite nicely, but they are fairly big. They are bulky items requiring ultra-low temperature often, and these enabling technologies. And what would enable wider utilization is the miniaturization of these systems.
Yeah, that's totally true, because we are talking about many objects, and each of them have a certain footprint. For instance, on a chip, and there are efforts to increase the density of the qubits, for example. And one way to do this is to increase the operating frequency of the qubits, which is currently typically in the gigahertz, tens of gigahertz range. And if one can go somewhat up, this means that you can decrease the physical size of the systems because of the wavelengths that are involved on the chip. Plus, you can also relax the condition of having that low temperature. So of course, producing these 10 millikelvin temperatures, which are the bread and butter for doing anything quantum these days, it's quite straightforward, but it's costly, and then it is very difficult to integrate large systems in those in those setups. So if you can increase the operating frequency by an order of magnitude, you can relax this cooling condition by the same factor, because what you really need in the quantum technology and quantum in general is that in order to have not a temperature determined state of the system, so not the thermal noise affecting your system, the temperature has to be much smaller than the energy of the qubit, which is the same as the frequency of these things. So there are a lot of efforts in trying to relax the conditions of very low temperature and also the size of the objects. But there is also a drawback in making things smaller and going to higher frequencies. Higher frequencies need really different technologies to control these systems. But it also means, small systems means that you come to the same problem as in classical electronics, for instance, that the power density is increasing, and you really run into the same problem of essentially overheating the system, although it may sound a little bit counterintuitive because you think that quantum is, in a sense, dissipationless technology, but in order to drive these systems, you usually need very strong signals. Otherwise, okay, let me step back. In a sense that quantum system, you want to make it very well isolated from the rest of the world. And this is what I was telling, that that's why qubits, they are developed to live longer and longer. But this also means that they are more and more difficult to address. So you need stronger and stronger driving signals, and this means that you start to dissipate heat everywhere around the thing. So it's kind of a very multifaceted problem that one needs to solve, and that's where we need a lot of workforce also. And
if we think about the kind of like active fields of sensor development, we have our systems for position, navigation, timing, but also like a lot of attention is now in gravitational sensors that are utilized to in an Earth observatory. Have you been active in these fields, or do you want to give some examples of gravitational sensors that are utilized?
My only experience in this field is actually somewhat non-technical. It is in testing another fundamental theory of nature, which is the general relativity, developed by Einstein some 120 years ago or 110 years ago, which describes how gravity works at its most fundamental level. And the better capabilities we have to test gravity and make gravitational field measurements, the better we understand also gravity in different situations. We don't have to create a black hole or go into the vicinity of a black hole in order to test gravity at a more precise level than ever before. At my heart, I'm a scientist still, even though I have been working in business operations for most of this decade. But what I think is one of the most exciting aspects of what quantum technologies can enable in the future is testing this kind of fundamental theories of nature, whether from gravity, whether we talk about gravity or quantum mechanics itself.
Exactly, and one of the quite intriguing, exciting topics that I know that Tommy, you've been working with is to use a qubit as detectors for dark matter. And I know that Jukka, you have a lot of collaborations abroad on this topic as well, and having 3D cavities for qubits to entrap the dark matter and using them as sensors. So could you enlighten us a little bit on that?
Yeah, well, I can start and then Jukka can continue from there. Dark matter is indeed a very interesting mystery of the universe, because what we know from astronomy and cosmology is that from the ancient times, in fact, before the universe was 1 second old, already at that time, most of the matter and energy density in the universe consisted not only of ordinary matter that everything here is built of, but for the most part of dark matter. That is some kind of matter component that exists in the universe, is abundant almost everywhere, but which we do not know what it is made of, whether it's a new type of particle or something completely different, such as a mini black hole or something. I have worked on this a lot during my scientific career, but what quantum technologies are now indeed enabling is to create new types of detectors for dark matter particles and other types of not yet known fundamental particles. How that works, maybe Jukka can tell you more about it, but in many cases the very idea is to use the same qubits that one can use in quantum computers to perform the computations in this context as detectors. But maybe Jukka, if you want to add to that.
About this problem, I can only say technologically that it's there are indeed, as Pauliina mentioned, some collaborations on this to really combine qubits with macroscopic, very, very high quality resonators in order to superconducting resonators. This is, for instance, a collaboration we have with the Fermilab in the US in this direction. So qubits can be also very useful in this direction. I think if you are coming close to the end, I wanted to raise the topic that excites me most currently.
Go ahead.
And it was, maybe it's already obvious to you, but for me, the most kind of fundamental thing in this business is how does quantum mechanics and thermodynamics interplay? Why do we have temperature in the universe in general? What makes a inherently quantum system which evolves unitarily? How can it really lead to something we have a temperature in this universe? So this is a thing that, as I mentioned, now we have the technology has developed. Developing quantum computers has given us a lot of tools that we can address problems, which in my case happens to be this one, and there are many others which quantum technology can us to look at in basic science.
Thank you, Jukka. Now in this chat, we have explored the quantum technologies very briefly and in a superficial level, of course. We explored the communications, we explored sensing with quantum, we explored quantum computing, and pressed the topic of workforce demand in the future. But if we think like summarize the talk, where are we now in honestly, and what we can expect in the next 5 to 10 years to see?
I think that even though there sometimes sounds like there's more hype than there should be, I still think that we are really on the verge of a big breakthrough, especially in quantum computation. In 5 years' time, hopefully, we have seen already quantum computing providing superb solutions that even the best possible high-performance supercomputers cannot provide in certain types of applications. Certainly not in every possible field, but maybe in specific fields, whether it was in materials research, material development, drug development, or in optimization that concerns finance or telecom or some other area. I would say that really we are on the verge of achieving it now. And in 5 years' time, that is only about to accelerate.
So get that in the writing, and if we come back in the 5 years, we are giving a new presentation to meet these challenges. But I think it's time to wrap up, and if you have any questions to myself or Jukka, Tommi, I think we have time for a couple. No, you learned everything you wanted to learn about quantum, and that's fair. I would want to emphasize that we have the quantum technology roadmap launching session next week, 27th of January. It's together with Business Finland, who is our partner in developing the technology roadmap. So if you are interested, please join, and please be in touch.
Thank you.
have. So try to find good place for you. This keynote session is going to be very popular. So please try to squeeze in as much chairs as you can use. Leave some places to people who are still coming. And we start in a minute. So welcome everybody to the keynote session of today's Space and Defense track. And I'm giving a short introduction about the history. We started with Satellite Workshop 2018. And 18, Finland has just got the first satellite in the summer of 17 and the first commercial satellite in 2018 January, around the time of the first Finnish satellite workshop. So time has been passed, and the world is quite a bit of different place nowadays. And Finland is launching satellites from the serial productions. ISI have been already launched more than 60 satellites to space, and Finland as a country, as a government, is starting or started to operate satellites as well. So we are going to dedicate this keynote session to Finnish own capabilities in space and governmental satellite as well. And the first speaker is going to be Major General Timo Herranen from Finnish Defense Forces, who is also in charge of the Finnish space capabilities for defense purposes. And after this speak, we are going to have on the stage Pekka Laurila from ISI, one of the founders who is standing behind all these satellites which Europe are needing at the moment really urgently. So, ladies and gentlemen, the first speaker of today's keynote session is Major General Timo Herranen from Finnish Defense Forces, also the Chief of Finnish Space Forces. So, welcome to the stage.
Thank you, and good day for everybody. It's nice to see so many folks here. Seems to be kind of almost overcrowded. Although I ain't gonna speak like all this fascinating stuff like black holes and dark matter like the previous presentations, but I promise I will mention at least nuclear weapons once. F-35, that ain't no spaceship, but why it is there is the fact that it's one of the capabilities which will use and uses space quite a bit, and it's also a tool to leverage space capabilities into a kind of a deadly fighting force, and that is why that is there. But let's go into the space. Space is relevant, it is real, and it is today. Space is safe for military operations as oxygen is for us humans. Often invisible, but mandatory for success. Ukrainians do not launch their long-range drones to Russian oil refineries without space. Israel did not seize air superiority in Iran in 12 days without space. And neither did the United States drop massive ordnance penetrators to Iranian nuclear facilities without space. Today, space is an arena for competition and cooperation. And cooperation is also mandatory for all, everybody, even the United States. New space has changed the space race for good, and new players and opportunities are rising. I will cover these three topics in my keynote speech here. First, a little bit about the military use of space. In my mind, space is about resilience, and it's also about leveraging space in all domain fight. For example, with the F-35, which is on the board. Time and precision are still mandatory enablers for military ops. Today, even we can witness GPS jamming every day just flying in eastern Finland, done by Russians, obviously. How it does affect your actions depends on what you fly or what do you sail in the sea. It can be taken for granted that if we fight, we will fight in GPS-denied environment, and we need to build the resilience to be able to deliver effects timely and precisely. Secure comms communication is a must. Satellite communication with increasing bandwidth enables us to build space-based C2 layer to supplement existing arrangements on the surface of the Earth. Mesh networks in space enable building cooperative space fleets. And how about network-enabled weapons and collaborative long-range capabilities? Satellite communication, please. For years, in the military, space has been used for strategy, intel, and so-called silos of excellence have been built in many forces. Today, space is present on operational level. Increasing number of space intel assets on many wavelengths together with artificial intelligence have increased the potential for tactical use of space. For example, should we fight drone fleet only by drones, missiles, rockets, and guns? A laser, perhaps? Or should we leverage space capabilities to shoot down the archers and arrow makers instead just focusing on arrows? To help doing the math, when Iran launched their attacks again with missiles and drones towards Israel, based on public papers, the cost of one single night of defense was $1.2 billion, which is quite a lot of money. That said, effective defense cannot be based on defense measures only. Fires, today's long-range fires require timely and accurate intel on tactical level. How tactical and real-time we can go with space, it is only a matter of volume and money, of course. The tech is there, we just gotta do the math. Shared early warning relies heavily in space, and the capabilities today are in rare hands. Counter space, should we just sit idle on our hands while our adversaries are putting all the effort there is to deny the use of space? And last but not the least, you can leverage space also for passive defense and survival. One real-life example. Based on National Security Space Association's paper, the United States used both the military and dual-use satellite images in planning and conduct of Midnight Hammer operation, where they dropped these bombs into the Iranian nuclear facilities. SATCOM was needed in coordinating 18-hour flights with the B-2 bombers between aircraft and command posts. Precision navigation obviously was there, not to mention the constant, continuous surveillance of missile threats from the space. Putting things together, to win, you gotta be in the space. Second, about competition and cooperation in space. Space used to be an arena for the big boys, United States and Russia primarily. In the last 10 years, China has accelerated full throttle, and Russia's unlawful war efforts have caused their space program to slow down. China has increased its space efforts around 600% in the last 10 years. People's Liberation Army has these days over 500 ISR-capable satellites, orbital intel, so-called repair satellites, whatever you use, and has demonstrated anti-satellite capabilities from ground and from space, up to a GEO. SpaceX being the ultimate launch leader, China has increased their launch capacity significantly and surpassed SpaceX in launch cadence, launching 3 Long March rockets in one single day. Albeit in downfall, Russia has still considerable space capability, including anti-satellite capabilities from MiG-21's missile launches to orbital to nuclear blasts. There are signals of China-Russia cooperation today, and unfortunately, being on declining curve does not necessarily mean a reduced aggressiveness. Oftentimes on the contrary. But today, the race for the space dominance is between the United States and China. There are European powers and NATO. NATO builds on national capabilities, offering oftentimes glue so-called glue between these national capabilities. Capabilities these days are oftentimes biased towards the United States. Regardless of our European efforts, talks about the European military space autonomy are premature. And there will be, and there is, need to cooperate with the United States in the foreseeable future. I think realism is a solid base for cooperation. To cooperate, you need to also to contribute and to seek mutual benefit. That is why we need to seize the moment and start building credible and robust space capability. More than long lead programs, we need practical initiatives bringing usable capability step by step. Instead of lying idle in the silos of excellence waiting to be launched, space has to be present in everyday exercises and everyday life of our forces. Today, not tomorrow. This brings me to my third point, new space. New space has changed this space game for good, I think. An example of this is last ISI satellites launch to LEO on Sunday, 11th of January. It's also pretty cool. I think we could...
And liftoff of Falcon 9. Go SpaceX, go Twilight.
Vehicles pitching downrange. M1D, chamber pressure nominal.
At T plus 30 seconds into flight, Falcon 9 has successfully lifted off.
There it is, and these guys are now orbiting the Earth in our control. Meanwhile, they do so, we are developing cooperative use of our sovereign fleets with the like-minded nations with similar capabilities. The more you have satellites on orbit for tasking, the more you have coverage, and the faster you can get the data to tactical level, which is one of my key goals. We Finns believe in resiliency. That is why I think that combination of military capabilities, sovereign or allied, cooperation arrangements between nations, sovereign and contracted commercial capabilities together is a solid base for building space capability. Commercial capabilities belong to every space nation's portfolio, be it United States, China, or Ukraine. Although, we must keep in mind that when the crisis emerges, or even before, dual use does not warrant immunity to counter-space operations. I think there is a great potential to develop space capabilities here in North, be it ISR, SATCOM, launch capabilities, SSA, SDA as a baseline. Doing things together and putting each nation's strengths together, we can be credible players in the space race. There is existing an emerging commercial market in the North Europe and also here in Finland. As you could see, there were over 30 companies on the board. ISI, Reorbit, Kuva Space, Aurora Space, just a few to mention. And if you bundle in AI, artificial intelligence companies, new space companies will, if you bundle in AI companies, you have quite a portfolio. I hope that unlike some traditional defense companies, new space companies will find a way to do business, not only competing, but augmenting each other in the space ecosystem. Also, we, in the uniforms, must update our ways and means to do the work. I think it is on now to decide how we utilize opportunities to gain upper hand against our adversaries. I do believe that existing and emerging opportunities in the new space will be a crucial part of the picture. And I'll end my briefing with the words of my good friend Buzz Lightyear, to infinity and beyond. Thank you.
Thank you very much. This was Timo Herranen, the Chief of our Air Forces. And next, I would like to ask to the stage Pekka Laurila, who is representing this new space. Pekka has been building the first satellite of Finland and the first commercial satellite of Finland and many other capabilities of Finland. So let's give an applause. Pekka Laurila, ISI founder and Chief Strategy Officer.
Hey, it's a lot of people. The 2018 workshop when I got to present the ISI X1 results was, I would almost say, like something that as an engineer I like more than giving more corporate presentations like this. But I'll drop in at least one equation if possible. So I would love to tell a lot what we're doing with the defense forces, but I'm not going to. So I'm going to tell you something else. So ISI, as Jan said, so we have now, let's say, built ourselves as a pretty big player in the global tech ecosystem. We are best known for the radar imaging satellites. So we build, design, build, operate synthetic aperture radar satellites that are the world's smallest, and then that also means that we're able to operate sort of commercially feasibly the world's largest group of these type of satellites. So that's how they look like today in the current generation. And what ability to access any location down to the tactical style timescales. And in the sort of absolutely highest level of abstraction, what do we mean by this, or where are we trying to go with this? Is that if you have that as the key piece of, or like the critical piece of the puzzle, then what you're able to build towards is kind of like finally the sort of infrastructure level reliability and availability of truly objective information about the world. So something that could become as much of digital infrastructure for the world as satellite navigation is nowadays, but just something that actually tells the live truth. And you do need those key building blocks. You need a lot more as well, but this is what we are on the path to building. And here comes the math. This is what you call CEO math. So in year 2015, when we spun out of the Aalto University, we were operating in the sort of hundreds of thousands in revenue scale. And then if we roughly double ourselves every year, then what that gives us in 10 years is the to the 10, which is exactly the 2024. So this is the scale that we are operating right now, and then actually this puts us on a trajectory where we have been like literally exponentially growing every year for the last 10 years into a pretty meaningful scale. And then now if you think of what are the sizes of let's say world's digital infrastructure kind of key companies like your Googles, they operate in the hundreds of billions of revenue scale, and nothing less should be the goal. And if you only double yourself for the next 10 years, there we are. And then if we switch to like us being halfway in the logarithmic scale, kind of more on the sort of linear scale, why am I here talking about sort of defense related matters is that you take any deep technology that becomes infrastructure for the world, internet, satellite navigation, that's the path that it's going to take. So you're going to be in academia first, then the major first use is governmental defense, then comes the big enterprise industries, finance, insurance, energy, so forth, and then further down the line, sort of like lower and lower kind of sort of transactions sizes, higher volumes, and then all the way down to consumer at the very end of it. So that is the direction to which we are growing, and on that path, you could say that on a kind of linear scale of let's say industry adoption, we are still on the beginning side. But the defense market, obviously, for technology like this, as said, is big. I think our statement is just that like it's luckily it is like this, that currently only 5% of world GDP is in the category of defense, and the 95% is in the category other, and then there will be a lot to grow there as well. But if you think of ISI as of today, being in that roughly halfway to there, so today we are a pretty global company, just a little short of 1,000 people. now around a little over 10 countries, and we do have a lot of customers in also countries where we don't have physical presence, and a lot of those customers, of course, are governments. So there's a lot of that linkage here. Headquartered here in Finland, second biggest site in Poland, third in US, in California, and we do operate satellites from multiple locations. We manufacture satellites in multiple locations. So in that sense, it is a very, very global company as of today. Yes, satellites have been made and launched. Also follows the exponential curve over here. So if you fit the same curve, give it another 5 years, and then we're operating, 200, 250 satellites. If you just fit curves over here, and it's probably not that far from the truth. We have committed to manufacture over 50 satellites over the 2026 time period, so that as a kind of growth path, it does kind of follow the scale. Of course, the technology moves forward very fast too, and we are not intending to stop by any means. And then also, we're not really intending to stop on SAR sensors only. But again, like I said, this is the path where we have established ourselves, from the very first satellite as the world leader, and we are doubling down every year as we go. And what does it give you? Like if you think of now, you have a lot of SAR satellites in space. Some practical examples is look, the way to think about the system is I put the dot on the map. I can start a real-time feed on what is actually happening there on the ground in a level of reliability that I don't have to worry about, meaning that like I'm not weather or any other sort of environmental condition limited, meaning that then the way to push this update rate faster is literally just to add more satellites. And then, as Major Helena General Helena just has said, it is really about kind of running the numbers. How much performance you need. It is sort of like a budget game. But you can keep an eye on things, and then different use cases have the requirement of what truly is real time set a bit differently. And of course, we can first start from the use cases where the real time is a little low requirement, but then when you go to cases where real time means literally single minutes or seconds, then of course the constellation needs to be larger. But again, completely achievable sizes. You're talking thousands of satellites, but we've seen SpaceX launching tens of thousands of satellites, so it's clearly not impossible. So the resolution scale nowadays, when we talk about imaging with radar, good to understand that it is not only blips on a screen, but it is a very high resolution imaging. So resolution cells can be pushed below 20 centimeters on the ground, which means that you're not only detecting things, but you are classifying and identifying things. And again, like doing this two things, of course, allows you to actually classify. And when you combine two things together, is that then the famous digital twins, or how would you call them, sort of like a sort of synthetic world situational awareness, is then of course something that kind of emerges out of this. That the aim is to be able to enable the interaction with this data more and more as semantic objects than pixels. And if you push this to the very extreme, this is also real data, monitoring a vessel's movement in literal second by second frames. It's something that we're able to do. Now, of course, there isn't enough satellites to keep a literally continuous coverage like this, but again, it's a numbers game. You could have that. And then pushing this now to the military world, when that situational awareness needs to be available in the context where it really matters on even tactical level, then that means that there are systems where you need to forward deploy. There are systems where you need to connect into the C4 systems with digital interfaces, because when the tactical timescales are starting to be in play, well, what happens is that really everything matters, like the way how you connect the systems together, suddenly you don't have the time to call or to print the paper because that becomes the bottleneck. So more and more these type of, let's say, end-to-end tactical system development is what we are working on. And in the end, what it sort of results in is this type of down to tactical timescales, sort of synthetic world situational awareness of what is actually happening there in your area of operation day and night, and then that being pushed to a level of accuracy that is valid for even the type of targeting scenarios that General Heronen was just referring to. This is an area where the defense performance is considered very important, and systems like this. Yeah, one another way to put words on how important systems like this are, though they appear to be needed around the world. And over the last 12 months, we've now, as ISI, signed over 1 billion euros of new sales of systems like this. So that is a part of that growth path, and we are sort of really trying to make the capability available into the places where the allied nations need this. And you're seeing a lot of flags of places where this type of capability built on a sovereign basis is really for the first time being built on the sovereign basis, and then there are some cases where this type of additional capabilities is considered something that gels into existing systems. But like a lot of this now that falls on us to also make sure is that we're not only creating separated bubbles of sovereign systems, but we also make sure that if the nations are willing to join and federate systems in a variety of coalitions, that then the technical capability of having that interoperability really is there. And in that sense, it's not that different than the F-35 fighter that you just saw there on the screen, that when you have multiple different governments operating the same technology, then the ability to make that technology interoperable on a coalition basis is, of course, a lot higher than if it's a different technological basis. So then this type of leverage, we're trying to make sure that all the customers can take advantage of that. And now to remind, if you look at the adoption curve, we're also trying to look further. We are not only working in defense by any means. I think it was last year when Shay was here on stage, showing our natural disaster solutions products, and this is something where the work happens mostly with the insurance industry. So again, like the next step on that curve. So we are being used by multitude of insurance companies and governments around the world to respond to natural disasters, and then here the revenue is sort of only tens of millions. So you're kind of seeing that like this is something that here the adoption still needs a little bit of a time, but what we are really trying to make sure that we are exploring in that market very actively. So companies like Tokyo Marine or Swiss Re, who are the largest insurance companies in the world, are the type of enterprise customers that we are working with. And also we try to do science. This is really cool technology, and sometimes we have to try our best to not do science, to focus on the engineering. But here's a cool example of the volcano eruptions in Iceland, where the sort of very rapid interferometry monitoring allowed to kind of keep track of the underground magma movements and then the build-up to predict the next fissure points. And then we worked on this together with the Icelandic Met Office and made it all the way to science as sort of new research from the point of view that this fast repeat rate interferometry on this kind of satellite scale had never really been used because it had never really existed. And then it did open a couple of new ways to let's say, replace the sort of in situ point measurement accuracy, to be sort of more broadly applied over the terrain. And And the other thing on the sort of civilian side is that if you think of like where is the market then on the civilian side, if defense is growing big, then how can insurance be even bigger? One example is if you think of these sort of natural disaster style use cases, then here's an example how in a single day we're doing 1 meter level mapping of the entire Florida post the hurricane, and then what that yields is ability to provide down to building level measurement of flood impact. And what does that provide is that if you take the horizon far enough, then you're able to operate in a world in which this type of sensing would become like the actual metric that can be used to define the insurance product, meaning what's called parametric insurance products, so that you can then remove the overhead of like actually valuing or inspecting the property actual, but doing it more as like a financial derivative, that if this threshold in this objective metric on a global basis is triggered, then the payment is triggered. And what that means is that world still has most of its properties that are actually not insured at all because of this type of overhead question, that most of the world properties just by number are actually so low value that the equation doesn't close. So if we could help close this equation, then what does the insurance industry get? Billions, like literal billions of new customers, and then of course world might get an improved quality of life if we can close those type of insurance gaps. So like examples of these kind of country or continent scale markets that you can really fix with objective real-time information produced from space, if you can push that infrastructure to the level of performance that really is needed for it. And of course that performance has not yet existed, but that's what we're trying to create. And as a final slide, things seem to be going well right now, but if you're putting exponential graphs on a linear y-axis, then what happens is that you can always see that curve. It really doesn't matter what you put on your x-axis, it's going to look like, now it's happening. But again, like if we push the horizon into the place where we actually want to go, if I cross out the years, to go 10 years forward, then we find ourselves in a place where we have actually moved exactly nothing. So in that sense, the sort of the type of a startup growth or exponential growth in these type of technologies is that the way to look at it is that if you're trying to do this, then the past will always look like exactly nothing, and the future will look like incredibly scary, and that's how it's supposed to be. So for us, the next 10 years of that graph, then it's going to involve more platforms, more sensors, way more analytics, more like tens of new industries, and that means that there will be also a lot of collaboration here domestically in Finland. As you saw, we are a very global company. We're with a lot of global partners, and then really trying to make that type of a system to become reality. So still some way to go. We are either somewhere or exactly nowhere, who knows. But it's exciting to see at least a lot more people around this industry than there was 10 years ago, that's for sure. So good luck to everybody.
So, thank you very much, Pekka Laurila, Chief Strategy Officer, ISI. Pekka, if you wait for a moment, if you stay here for just a moment, so these are rare occasions nowadays when these kind of international new space stars are available for the home audience. So if you bear a couple of questions, so audience, you have a very rare occasion to put a couple of questions to Chief Strategy Genius behind all this growth right now, right here. So any questions? Yes, we have one question there. And if you cannot answer, if you don't want to answer, don't answer.
Yeah, this is pretty general. So how How do you see open source in this industry?
Is the mic is not still on? You can hear me? Oh, yes, okay. So I think there's a lot of similarities here, where like if you think of the current, say like the AI growth right now, that like a kind of realistic observation is that the source is a little bit more closed than it necessarily used to be in the past, and then there's a lot of things where, again, because the technology right now like lives in the phase of getting integrated into governmental and defense decision making. There's of course a lot of things where the underlying source of a variety of things cannot really be open, but at the same time, like there's a fair amount of the sort of interoperability standards and way how the data gets processed and so forth that like absolutely must be open, because then otherwise the industry cannot evolve. And there we are very much proponents of making it happen. So ICEYE satellite, flight software will never be open source, I can guarantee. But then, for instance, like ability to deploy radar data processing from level 0 to the forward, I think it's very realistic that like we will want to have also open source projects, to enable the sort of industry at large, to really take advantage of the infra. Yeah.
Thank you.
Thanks.
Is there another question? There is one.
Thank you. So you have now more than 60 satellites. You are planning on having more. How do you plan on reducing the risk of collision, because the space is getting busier and busier in LEO orbit? So what's your plan?
Yeah. So first we have to learn how to avoid all the Starlink satellites. The baseline, of course, of collision avoidance in general is that yes, we do want to maintain a constellation that has active propulsion. So we have the capability, and again, like when you go to the defense world, there are even other reasons why to have evasive capabilities than just debris collisions. But then, like, how does the world survive this? Then of course we'll need the sort of space situational awareness and open data sharing to be extremely good, because of course, like, you can manage, like we know from, say, air traffic control that if you actively manage even very congested airspaces, well, then they are extremely safe. But it does need that active management part of it, and we are luckily not yet in that place where the congestion is that bad by any means. But then if we want to be in a place where we help to avoid those collisions, then building the infra for the space situational awareness, not only US-based, not only Europe-based, but like global-based and multiple systems that really allow the high level of accuracy and reliability, so that then you can build safe operations on top of those systems. There should be more of this. We are completely capable to automate collision avoidance on our side, but we do need to get the alerts. Like, we are not going to be monitoring the entire space around us.
Thank you very much. And we have short time, so we have 2 more, and then that's it. So if we can have microphones there. No, Tommy, you are not going to get the question for this round, because you can just catch Pekka on the coffee break. Yes.
Thank you very much. Thank you very much for a very interesting talk. Obviously, you are growing very fast, and the scaling is the one thing. So what do you think in future, pretty soon, you need to have fabs for the satellites, or you need to have a huge data centers to process this data? So what do you see that, what is the biggest bottleneck or challenge in your scaling?
Yeah, I mean, the aim, of course, of any good engineering company is to make it make it so that at any given moment the bottleneck is sort of different, that you're never for very long dealing with the same bottleneck, but sort of, you know, examples of bottlenecks that there may exist at the different points in time is that, you know, for instance, currently launching satellites to space is sort of like a non-trivial logistics part. It may become that, oh, okay, so there will be just, you know, starships going every day, and then it's completely trivial to get the, you know, the mass to orbit, and then you don't have to worry about it. Right now, you know, what forms a bottleneck is that, you know, pragmatically speaking, if you want to scale by 10x, you're going to be waiting for 18 to 24 months to be able to get the new rockets up. So it's not sort of instantaneous. So that's an example of a bottleneck that has like a, you know, time lag to it. You know, world has probably, you know, enough capability currently to make rockets. You know, SpaceX does them a lot, but they just don't, you know, come up to the launch pad on schedule in as fast as like you could react immediately. There's a lot of like just like normal kind of physical industry related things, you know, component orders, deliveries, so forth. They don't happen from one day to another. You might deal with delivery times that are longer, so that means that the bottlenecks for scaling become kind of time lags. And you know, same thing goes for personnel, that, you know, you don't from one day to another get a new expert to ramp up. You're dealing with, you know, 12-month style timelines, you know, to make that happen. So most of the bottlenecks that we are right now dealing with, you know, have this sort of varying degree of how forward-leaning you're able to invest into things that will turn into real performance somewhere, you know, 1, 2, 3, 4 years down the line, and, you know, with what level of, let's say, business confidence that deploying the resources now, you know, to enable something in 2 years or 3 years' time, it's actually really difficult kind of equation typically to manage, and you typically end up finding that you know, you were 20 to 50% too short on your investments, but also, like, you know, there can be that one day when you find out that you were 2,000% too heavy on your investment 3 years down the line, and then, you know, this is the kind of like the part where you have to manage the resources responsibly. That, like, you know, especially if you're growing fast, the way how you drive into a wall can be also very fast.
Okay, thank you very much, Pekka. I think we are stopping here because time is running, and I hate to stay between lunch and people. So once more, big applause to Pekka Laurila,
thank you,
Chief Strategy Officer of ISI. I have also a few announcements. So now we're going to the lunch. We have 2 restaurants, Reima and Mezzo. Both work. In Mezzo we have a buffet for salad, so come along. In the evening we're going to have a poster session again. Coffee breaks are sponsored by Messukeskus. The evening program is sponsored by Exolaunch, Bitium, Elisa and Nanovac. And after the cocktail party here, after the poster session, we're going to have a sauna session in Laude as well. Everybody are welcome, and you don't need to go to sauna. We have lounge area, we have some snacks, we have some drinks, so you can just like mingle and have a nice time there as well. So I hope everybody will enjoy the conference, and we will continue with that defense and space track after the lunch in Lumituuli.
cooperation or coordination, especially with the WRC and with NATO. Today we'll look into the world of spectrum management, and if that's not familiar to you, it means that we regulate the spectrum because it's a natural resource that is limited, and our modern society heavily relies on it, so we need to protect it so that we can use it efficiently. We'll first start off with a little bit of background information with spectrum management and the radio regulations, and then we'll move on to the actual topic of the World Radio Communication Conference and what will be addressed there next year. But we don't have a lot of time, so let's get going. Spectrum management is the operations where we enable the efficient use of the radio spectrum. And depending on the source, electromagnetic radiation below 3000 gigahertz is regarded as the radio spectrum. Trafficom, as the national authority regulating the spectrum, has allocated the frequencies between 100 hertz to 400 gigahertz, so only a smaller part of that said radio spectrum. In Finland, we are bound to, or legally bound by, 3 different levels of regulation. We have the national level that we do, then we have the EU level that aims for harmonization and etc., and then we have the global level of the ITU that we'll talk in a bit. And that's because electromagnetic radiation, as you believe, the emissions are quite hard to contain within our national borders, so we need the international side of it too. And when we look at satellites, those are truly international, so we cannot do it only locally. Then we also do a lot of cooperation with CEPT, which is the European Organization for all postal and telecommunications administrations, and where we find common ground on regulatory issues, and naturally nowadays with NATO too. And just as a fun fact, in Finland, 99% of all radio transmitters are below 10 gigahertz. So this is an even smaller part of the spectrum, and it highlights how much there is competition for those easily available or easily accessible radio frequencies. We get our national jurisdiction or mandate to do this from the Finnish law, but internationally we get it from the radio regulations, which is an international treaty done by all countries and agreed by all countries that is basically international law governing the use of the radio spectrum. It is maintained by the International Telecommunication Union, which is a specialized agency of the United Nations and actually predates the UN, turned 106 last year. But like I said, it's maintained, so ITU doesn't do it. It's the member countries of the ITU that does it, and therefore it's legally binding for the member countries. It is the set of rules and regulations that dictates the use of the radio spectrum, and actually also some of the orbits around the Earth. And this is really important in the domain of space, because in Finland, within our borders, we can do pretty much whatever we want with our frequencies, but once it crosses the border, we need to follow and oblige the radio regulations. These regulations are updated every 4 years at the World Radio Communication Conference and can only be updated there by the member countries. And the outcomes of the conference are done by consensus, so no voting, which basically theoretically ensures that all the participants agree with the outcome. A little bit more about the conference. So the next one will be held in Shanghai next year. And the agenda items actually for that conference were already decided in 23 in Dubai. So that's a 4-year gap of decided agenda items that cannot be changed anymore, and 4 years of studies for those. And in Shanghai, the agenda items for 31 will be already also decided, and actually about the cycle, it is quite long. The agenda items for the 31 were already proposed in the Dubai conference in 23, so that's 8 years in between the proposal of the agenda items and the actual conference. So the cycles are quite long, and it can easily take 10 years to get your updates to regulations. But now let's get to the actual topic with this ugly slide where we have all of the agenda items that are addressing the radio regulations and what kind of updates we will potentially have there. As you can see, quite a lot of stuff there. Today we'll address a few of those. I won't go through all these, but a lot to go through. 19 items only for the changing the regulation. What I've chosen for today are 3 agenda items there. And let's start off with 1.5, which is extremely relevant today if we look at what's happening in Iran right now with all the demonstrations. This is an agenda item that addresses the unauthorized operations of Earth stations. So basically, the background of this is that the government of Iran proposed this and is really pushing this topic because they want to have, the radio regulations as a mandate to outlaw the use of Starlink within their national borders, which is kind of typical activities for an authoritarian regime to control the access to internet. This item potentially would increase the amount of strict rules to follow within the procedures of the ITU, and we do not support having more and more of strict rules in the processes because they are already complicated, and this would further complicate getting all the licenses, etc. Then the second item there is 1.7, which is not a satellite topic. It's actually an IMT topic, so which means all the cell phones, normal regular mobile phones, and 4G, 5G networks. But it relates to satellite topics, because if we look at one of the bands that would be opened up for IMT use, so the goal here is to get more frequency bands for normal cell phone networks. One of those is the 7 to 8.5 gigahertz frequency band, which might be familiar to some of you. It's used, for instance, for X-band satellite communications and remote sensing. And this topic is extremely challenging because depending on what side of the subject you look at it, your opinion is a little bit different. So, of course, the IMT side hopes to get more frequency bands available, but then also on the satellite side, there is a little challenges because those systems want to be protected, and this is a topic that is really important for NATO. Then 1.13 is an interesting topic because we've seen a lot of new solutions on the direct-to-device connectivity side, and this basically means that your own cell phone is connected to a satellite. There are some commercially available solutions, not in Finland yet, and this item aims to get an allocation for direct-to-device connectivity. We support the studies that are aiming for an allocation because that potentially could give more access to the service, because businesses potentially could be more open to consider that line of business. And then it would also protect existing systems within those frequency bands because we have then found common ground on how to have the allocation. Those were a few topics that are addressed in 27, but let's look a little bit further and go to the 31 agenda, or preliminary agenda. So these are proposed items that came up in the 23 conference. There's already 14 of those, so quite a lot. But one of those is extremely interesting for Finland, and is the 2.13, which is an agenda item that addresses the use of space-borne synthetic aperture radars within the X-band. Quite familiar for Finland. And this agenda item opens up the possibility to have restrictions on those services. It is an item that is proposed by some Asian countries, such as China, and Europe and Finland. We don't support addressing this topic because it was already addressed before in 2015, and there was no problems found out. And we haven't gotten any evidence on synthetic aperture radar systems in orbit causing any interference on Earth. So we do not believe that this is a topic that should be addressed at the conference, and we believe that it should be removed from the proposition. This was a very surface level, quick look into the different topics, but I just want you to take home from here that these are important topics that have potentially a huge impact on the Finnish satellite industry and other industries in Finland. So just pay attention to these because they can have an influence on businesses and the governance. But don't worry, there is still a possibility to voice your concerns, participate in the preparations. We are still doing the national preparatory work for Shanghai conference, and if you're interested in voicing your concern or saying what's on your mind, please contact us. And we have these meetings left where you're able to tell us what is the issue, and we can see what we can do for you. But thank you. That was a very quick one, and let's see what happens in Shanghai.
Yes, thank you very much, Otto Juukunen, and for the VRC overview by Traficom. Thank you very much yet again. And then we are waiting for the next presenter, would be Paula Breda. And how could the EU Space Act impact the satellite business?
Thank you. And the presentation as well. Well, while we wait for the presentation, my name is Paula, and today I'm trying to present you a couple of answers that I gave myself related to the topic of how is the draft of the European Space Act impacting our satellite business? The reason behind is that, well, I'm an aerospace engineer. I work for a spaceport, so I support launch services and launch service providers, which means if we have regulations that affects the satellites, then it will affect ourselves as well. Now, presentation is a bit weird. I don't know exactly what happens. But I know that by putting myself into this regulatory framework section, I am now in a lion's cage. So let's see what comes out of this. While we wait for the presentation, the second one is just a recap slide related to the draft of the European Space Act that's given by the European Commission. It was released in June 2025. It's important for the non-legalese, the engineers, that's a draft, which means it's binding. It's not binding, sorry, it's not yet. Here we are, perfect. And it's based on 3 pillars, which is the safety, sustainability, and resilience. Now, what I wanted to understand is how this thing is affecting my business. Remember the launch side, but also through our customers, the satellite business. And yes, it works. The first thing I asked myself is trying to understand who is affected. So as you see, space services providers that are offering services within the EU, but also those international organizations and space services providers outside the European Union that want to provide services within European Union. So to my business, everyone will be affected. It will have an impact on the launch business too. Now, I will answer the question whether we are affected or not as a launch operators and spaceport by taking a little the route. As you see, when we talk about satellite and sustainability, it's not only congestion of space. I just put these 2 plots. I took it from the ESA Space Environment Report 2025. As you see, we had an increase in commercial satellites that have been launched into LEO orbit starting 2020. Of course, corresponding to the mainly to the Starlink constellation for communication. But this number is tending to grow up. And the main question is, how do we bring the payload into space? Well, this is given through launches and launch operators, meaning the launch capabilities still have to be considered within the sustainability framework. And indeed, the European Space Act says that the term space services also include the launch services and whatever is around the spaceport, including maintenance and entire operations. So we are covered, that's good. Now, there was a consultation where everyone could provide feedback to the draft EU Space Act, and that's closed in November. It's online, so you can Google it, and you will find more than 100 feedback collected. So I created some statistics. We see more or less 66% of the responses come from Europe. We have strong responses from France, Germany, Belgium, Italy, and then let's say the rest. But interestingly, 33%, the remaining 33% from the non-European countries is mainly due to the US in several forms, government, but also companies. And then we have also some specific percent, 7.8, from Japan, which is also interesting, and then the rest. So I took some time just to see what are the positives and the negatives that have been taken from these companies or in general from the governments. I'm not going to present all of them, but I try to organize this with a couple of examples. For the European stakeholders, I see that we are very strong and positive for what is related to the support of this harmonization of standards, creating a common guideline, because each nation is doing their own national space program, so it is good that there is a baseline to follow, also in terms of reaching sustainability goals. However, I found several points. Here, there are two of them, the most important one actually that affect my business. One is the potential disproportionalities that can affect startups and small, medium enterprises by complying with these rules. And then there is also an unclear timeline to implementation in some of the proposed rules that are, for example, related to technical standards that shall apply, or also to when a specific sustainability rule shall come into place. Which means that a startup or SME may consider whether we would like to commit the money already, the budget, to be compliant with it a midterm for something that is not being clarified yet. I would rather use the budget, perhaps, to sustain my R&D and finalize my prototype service. Two examples. The first one I took is Amazon. It was filed by Amazon SARL, so the Luxembourg one, but the parent company is, of course, the US. As we know, they provide GEO broadband satellite constellation, Amazon Kuiper. They have more than 3,000 satellites in this constellation. So they all provide positive feedback in terms of harmonization. It shall be good also for the large constellation. However, since they are coming in with a big constellation, they see a higher risk related to the cost for compliance and reporting, mainly due to the accumulative assessment for the constellation risks, but also for debris mitigation that will apply to the entire constellation. Plus, there is also the risk that we fall into some duplicative rules, meaning our timeline will be longer, for example, to comply to the EU Space Act, but also to the national level, like within the Netherlands, that they already have a national framework for constellations, but also to outside the European Union, for example, from the US, increasing, therefore, the administrative burden. Second one I took is the Orbit. It's the Italian one for space logistics, orbital transfer vehicle, their carrier Ion. They deploy satellite into different orbits. And these are one of the guys that provided a negative feedback related to the disproportionalities that they could see for small, medium enterprises when being compliant to the new potential regulations on the three pillars of sustainability, safety, and resilience. For the non-European stakeholders, there are other pain points. In this case, funnily enough, most of the feedback was filed by the US. So it's a little bit driven towards that direction, probably, because they provide most of the services, application services to the rest of the world too, still. The first one is some sort of uncertainty related to the authorization, because the European Union could have, through their bodies, the power to perform more investigation related to the suitability of vaccines to the European market, and provided also additional sanction. So they will potentially not know if they are able to provide those services to the European customers. That will come along with higher compliance cost, which was actually one of the pain point also for the European stakeholders. And then, as I mentioned also before, there is this fear of having duplicative compliance, both in terms of technological standards or consolidated standards, for example, in terms of debris removals that have already been used, where perhaps the EU will be more restrictive, but also in terms of national regulations, perhaps from what the US has already approved, then it has to be revised and reapproved again from the European Union and then whatever European country we are dealing with. Two examples, Spire Global, they also have subsidiaries in Europe. This one came from the US. They offer space-based data and analytics, and they have their own constellation. I picked this feedback because they provided a little bit of quantification in their costs. So they foreseen that their manufacturing cost could increase of 10%. And what is interesting to me and my business is the launch cost. They foresee an increase for them in 20% to be compliant. In this case, the burden would be mainly related to the additional life cycle analysis or the cybersecurity assessment or the e-certification, and also redesign of specific components of a satellite. The penalty or disadvantage of not being into the European Union as an actor could be the exclusion, the risk of being excluded for the European market, and this duplicative compliance that I was mentioning before. Similarly, I took GSGSat, Canadian company. They provide services for greenhouse gas emission monitoring. I used this one because they have a constellation, but it's very small. I believe there are 13 satellites. There are tens of satellites, not 100 or 1,000. And they have the fear that there is a disproportionality in this act related to those constellations that are not huge, that are not in the hundreds or in the thousands. Plus, they provided the concern that there may be additional costs for those service providers that are actively involved into Earth observation as operators due to, for example, the environmental footprint or additional life cycle analysis that are due to this kind of services. And similarly, as before, penalty or disadvantage could be the authorization uncertainty, but also the application of compliance. Oops. Now, I got to the conclusion. I tried to give some answers to this question to myself. So how could the EU Space Act impact the satellite business, but also the rest of the business that is not only the satellite? The first one, I think, is that we could lose the availability of some non-European services, which means we better be quick to develop our European services to cover up that potential lack that we don't know yet about. This is because the non-European service provider could fear that there's not being able to access the market could be some sort of penalty. So they would prefer just to go somewhere else in the world, say, the cost that we introduce by complying to the European regulation could be like a threshold or a penalty to pay in order to be able to make business with us in Europe, which may not be too attractive for the rest of the world, apart from ourselves in Europe. The second one, rather obvious, some expected significantly increase for cost for compliance for satellite operations and operators. They also will extend to their users and launch operators in different ways. It's not, I couldn't find out still on which percentage, because it really depends how big is the company, and it goes back to this disproportionality towards startups and SMEs. And then I took the example of the large, or of the constellations in general, where it's still unclear how the impact will be on constellation owners or those service providers, whether the constellation is big or small, and then there is also an additional threshold put into the European Space Act of about 2,000 satellites, above which there will be more restrictions. Last point, and then I leave you. I think that we shall not risk to undermine the competitiveness inside the EU market by creating the new regulation. What I mean by this is that we see that we have a very flourishing environment in terms of startups and SMEs in the space sector. And they are still developing, most of them, they're still developing their technology and prototypes. So by creating a strict regulatory framework on it in order to enable this market, we may risk that this it takes longer, so we will reach it, but we will be already far behind to the rest of the world. Or this company may be forced, or will be more convenient for them just to move somewhere else in the world to the business there and then perhaps come back to Europe. That would be a pity. And that was it. I know there is a little bit of engineering taste in this presentation, but I will be open for questions. Thank you.
Thank you for Paula Breda on how could the EU Space Act impact the satellite business. Thank you for the presentation. And next up would be Tero Poutala with Quo Vadis in space traffic management, governance or coordination?
So, good afternoon, everyone. It's a pleasure to be here, Otaniemi, Dipoli, again. My name is Tero Poutala, and this presentation is partly related to my doctoral research. So, today I would like to ask a very simple question. So, where are we now, and where are we really heading in terms of space traffic activities? And my main argument is pretty straightforward. Even though the term space traffic management is quite widely used, we do not actually manage space traffic in a classical sense. At present, we don't have any explicit universal rules for space traffic operations, and there is no established explicit coordination mechanism for that activity at international level. What we do see is instead a mix of fragmented practices, limited information sharing, and very different approaches to managing risk. I will argue that we are currently in what I call maybe a pre-coordination phase. Perhaps some realistic progress, at least in the near future, I think, lies in a coordinated, in a structured coordination, not in a full supranational governance or management or control. This situation is closely linked to the current international legal framework for space activities and to its limits. So first, what is space traffic management? The idea is not new. It was discussed already in the 1980s. Many writings related to the topic presented much before. One influential, maybe perhaps more of an academic definition comes from the cosmic study on space traffic management, and it defined space traffic management, STM, as the set of technical and regulatory provisions for promoting safe access into outer space, operations in outer space, and return from outer space to Earth, free from physical or radio frequency interference. More recently, the European Union adopted a more broader definition in 2020, and it describes STM as the means and rules to access, conduct activities, and return from outer space safely, sustainably, and securely. So in simple terms, STM refers to technical and regulatory measures that support safe and secure and sustainable space operations. However, there is some level of problem. So the word management suggests, at least to some extent, a centralized control. Maybe something a bit similar than in air traffic management, in maritime traffic management, or road or railway traffic control. And that model perhaps does not match how space activities are organized in the international plane. So legally, politically, or technically. And this mismatch between the term or the concept and the reality is one reasons why the debates on the STM often stall. So, despite these conceptual issues, the need to address space traffic is relatively clear, at least from my angle. So the main drivers are well known. So first, we are seeing rapid growth in satellites. We have seen and we are seeing large and mega constellations. Second, there is a steady increase in space debris and collision risks. And third, I believe that the modern societies are increasingly dependent on the space infrastructure, such as navigation, communication, and Earth observation. And in short, so congestion, debris, and dependency make the current situation pretty unsustainable in the long run. And if we look at the current international legal framework, at least the picture is quite clear. The 5 UN space treaties and the associated principles to couples do not address the space traffic management explicitly. At the same time, states or regional actors are not inactive. Some, like United States, are taking domestic action or have taken, and as well as the European Union has proposed its own rules. In practice, I would say that the today's system of traffic management in space sector looks something like this. So, space situational awareness and tracking data are provided by a number of different actors. Conjunction warnings are often issued unilaterally. Maneuvering decisions are taken independently by operators. Debris mitigation measures are applied unevenly. So the key point is that the information mostly flows in one direction with very limited amount of shared practices and procedures. And the operators are informed of risks, but they do not coordinate in a systematic manner their responses. Perhaps it's not even coordination even yet. Maybe it's better, can be described as some level of informed coexistence. And calling it management or stable coordination probably overstates what it actually exists today. So what would a more realistic approach look like? So a report from 2018 Espi suggested that the STM consists of 3 complementary functions: understanding the operational environment and in identifying risks. Secondly, setting the rules to ensure safety and long-term sustainability. And thirdly, organizing cooperation among different actors. And most of the current efforts, I believe, are focusing on the first function, i.e. the monitoring. And the real gap lies, besides the regulation, in the coordination, at least in the operational level, in a systematic coordination. European Union provides a useful example of how these issues are being addressed in practice. And through the EU space surveillance tracking, the EU is already supporting awareness of collision risks. Coordination is increasingly organized at EU level through relevant EU institutions and certain domestic actors. The EU's Draft Space Act is building on that existing structure, and it's setting common rules, if approved, on safety and sustainability, including the collision avoidance and debris mitigation. Interestingly, in relation to the topic of this presentation, the Act does not explicitly use the term space traffic management. Instead, it's addressing the issue indirectly through orbital traffic rules and coordination mechanism. So, same subject matter. And the Act, the Draft Act, includes a dedicated chapter on orbital traffic rules and also applies certain requirements to third country service providers, which could perhaps then extend the influence of the outside the EU. However, in the end of the day, it's still a regional solution, if accepted. And in any case, if that would be the case, it's likely that it would improve the coordination within the EU, but still it wouldn't create a global STM system. And this is important because if you think about the space traffic, is inherently global, and regional rules cannot reach that in full. To conclude, the STM debate often skips an important step. So before asking whether the space traffic should be managed or governed, I think we first must ask whether it could become coordinated. And at this stage, strengthening structured coordination regionally and perhaps gradually internationally is likely to be necessary, as well as to some extent realistic, I believe, if we are taking, let's say, some clue from the ITU framework on spectrum management coordination at the international level, for instance. So in this sense, the proposed EU Space Act is taking, I believe, appropriate and useful steps to address the existing regulatory gaps. Through its potential Brussels effect, as advocated by Professor Anu Bradford a couple of years ago, I believe that the EU Draft Space Act, if accepted, may influence practices beyond the EU, or maybe that it wouldn't. Let's see. Whether this will eventually lead to a global governance of space traffic management, or even true traffic management, I think that remains still pretty open question. But for now, I believe that the coordination is the essential foundation which needs to be reached before. Thank you.
Thank you very much, Tero Poutala. And for the Quo Vadis in space traffic management, governance or coordination. And before we start for the next slide, we will have just a few minutes for our technical side to fix the issues with the presentation, but then we are going onwards, so few minutes. what format do you want? Do you want a hand microphone? Do you want a headset? Or do you want from the booth? Yes, of course we can. Yeah. So, a moment. So we just fix over this presentation so that we get it properly working, and then we start on. So, but as said, like a few minutes, if you're fine with that.
So your next presenter. Yes. We can go have a look, see how things are.
Yeah. Okay. Yeah, we can do that also.
Okay. Relax. Why is showing things on the top?
Okay, it's the PDF, the menu. Yes. Software menu. Don't ask me why.
Can I somehow close
Do you
it?
want to reset just the whole thing?
Should not.
Aha. Okay.
Why is
Interesting. Yeah, it's showing. Okay. I don't know.
Do I need to click it? No.
No, 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 no. It's not going well. Is it the alt menu? You can alt. Nope.
No.
Nope.
What do I do? Nothing? Just keep it?
The question is, will it flow?
She can click the thing and Indiana works.
Okay, if you are okay, then we can start on.
Yeah.
Okay. And next up is Aisha Hörtä and drawing analogies between maritime and outer space, or in the governance of ISR activities. And Aisha, stage is yours.
Mic test? Can you hear me all well? Lovely. Okay. Good afternoon, everyone. Like said, my name is Alicia Hörtä, and I'm a third-year law student at the University of Eastern Finland, and also the president of the Finnish Space Law Association. Small warning beforehand, I'm not presenting myself as any expert on the topic. What I'm sharing today purely reflects my own research and analysis. It hasn't also been peer-reviewed, so please take everything with a grain of salt. It's also the first time presenting with a bigger audience, so please go soft on me. That said, the topic I'll be speaking about today is drawing legal analogies between maritime and outer space law in the governance of ISR activities. I can't get the next slide. So when naval vessels conduct surveillance on the high seas, international law has a lot to say about it. But when a satellite does the same thing from orbit, much less so. So the main question of my presentation is whether the United Nations Convention on the Law of the Sea, i.e. UNCLOS, can help us understand how ISR should be governed in outer space. In other words, can a domain where due regard is operationalized offer guidance for one where it remains largely abstract? Now, first, I'm going to begin by unpacking the concept of ISR, because this distinction matters in legal and operational analysis. Intelligence refers to the information that has already been processed and analyzed. It's not raw data. What matters, however, is that intelligence transforms that data into actionable insight, which supports strategic planning and operational decision-making. Surveillance is continuous monitoring over time. The purpose of surveillance is to detect changes, track movement, intercept signals, and provide early warning of potential threats or developments. Lastly, reconnaissance. It's usually more focused and short-term. It aims to gather specific information about a particular area, object, threat, often under time-sensitive conditions. Now, traditionally, space-based ISR has been dominated by state-owned and classified military assets. However, today we see a significant shift towards commercial ISR. And although these commercial products are often marketed for civilian or non-military purposes, they're frequently used by defense departments, intelligence agencies, and civil law enforcement. And that brings us to the dual-use environment. From a legal perspective, this blurs traditional distinctions between civilian and military space activities and complicates the legal questions. Now, as lawyers, we love to regulate stuff, so unfortunately, we have to take a look at the legal frameworks. In the maritime domain, we have UNCLOS. It functions as a legal rule book for the for the maritime. It governs stuff like navigation, overflight, and surveillance, and it does so through a combination of rules and obligations, etc. In outer space, the equivalent is the Outer Space Treaty. It establishes that outer space is not a subject to national appropriation and that is free for exploration and use by all states, provided that those activities are for peaceful purposes and for the benefit and interest of all countries. Now, related to ISR specifically, we have the remote sensing principles, which were adopted by the UN General Assembly. They recognize the legality of Earth observation from space, but they emphasize the respect for sovereignty and legitimate interests of the sensed states. However, it is very important to note that these are not legally binding. They are guiding norms rather than enforceable law. So both the UNCLOS and Outer Space Treaty, they regulate these domains described as the global commons. They are the high seas, deep seabed, atmosphere, Antarctica, and outer space. The global commons, they are areas beyond national jurisdiction that are accessible to all states. In both these regimes, states enjoy freedoms such as navigation overflight, but these freedoms are not absolute. That brings us to the key question: what's not allowed in remote sensing? At first glance, space activities may seem unrestricted, but remote sensing is not a legal free-for-all. That means that we have to look at Principle 4 of the remote sensing principles, which emphasizes respect for state sovereignty. So even though satellites operate from outer space, the data they collect concerns resources, territory, and people on Earth. As a result, all remote sensing activities must respect the full and permanent sovereignty of states. In practical terms, this means that states should not conduct remote sensing in a way that harms the legitimate rights of interests of the states being sensed. Secondly, we have Principle 3 of the remote sensing principles, which reminds us that remote sensing must be carried out in accordance with international law. This means we have to follow the UN Charter, the Outer Space Treaty, and the rules of International Telecommunications Union. So ISR from space sits in somewhat of a legal gray zone. It is not prohibited as such, but it's not unrestricted either. We have some principles and rules. The starting point is Article 2, Clause 4 of the UN Charter, which prohibits the threat and use of force against states' territorial integrity or political independence. But simply collecting information, even though it were for military purposes, does not by itself amount to use of force. However, problems do arise when ISR enables or supports coercive action. This can be persistent surveillance, targeting support, or real-time intelligence that directly facilitates military operations. And these can be perceived as part of a hostile act, especially in times of heightened tension or armed conflict, as we are in currently. Water break, sorry. This brings me to the concept of what we call due regard. In both UNCLOS and the Outer Space Treaty, freedoms are explicitly limited by an obligation to exercise due regard for the rights and interests of other states. The main problem in the Outer Space Treaty is that due regard is entirely normative. There is no standing international body with authority to authorize, review, or sanction ISR activities, which means compliance is very decentralized and self-judging. States themselves have to decide what constitutes sufficient regard for interests of others. So, although the Outer Space Treaty includes a consultation mechanism under Article 9, it is voluntary, so states don't have to follow it. Therefore, due regard remains a principle of good faith rather than an operational rule. By contrast, UNCLOS embeds due regard within its operational system. So under UNCLOS, freedoms on the high seas are exercised within a dense institutional architecture. The IMO develops binding safety standards. The maritime safety information systems disseminate navigational warnings and notices to mariners. and disputes can ultimately be brought before international tribunals such as the ITLOS. This means that due regard on the high seas, it's not an abstract obligation, rather it's expressed directly through procedures, notification standards, and records. My key argument of my presentation is that this maritime model can inform the governance of space-based ISR without fundamentally changing the Outer Space Treaty. In practical terms, this could be operationalized in 3 layers. First, at the pre-mission stage, states and licensed commercial operators could issue standardized orbital activity notification, which is analogous to the notice to mariners. These would contain only safety-relevant information, such as orbital regimes or planned proximity maneuvers. They don't require consent and wouldn't obviously reveal any sensitive intelligence details. And the purpose would be to demonstrate good faith coordination and create a legal record of due regard. Second, during ongoing ISR operations, internationally agreed technical standards could define what constitutes safe or non-interfering conduct. These could include minimum separation distances between satellites or advanced notice periods for close approach operations. Lastly, in post-incident situations, these notification and maneuver logs, they could be used to assess whether a state acted with due regard. Even in the absence of centralized enforcement body, which we don't have for outer space, these records would function as evidentiary tools, much like the maritime safety information does in maritime dispute resolution. Crucially, my approach balances secrecy and legality, so ISR missions would remain classified in substance while still applying and complying with procedural expectations. What makes my model better is that it doesn't require a new international enforcement body, which is politically unrealistic. Instead, it uses procedural tools we already know and that exist and adapts them to outer space. Even if there's no central authority, states can still rely on maneuver logs and notifications to demonstrate compliance under OST Article 9 in case of disputes. So what I'm proposing is it's not regulation that slows down ISR, it's a light touch coordination that lowers the risk of harmful interference, and that matters due to international humanitarian law. So unlike the maritime domain, we simply don't have a centralized and legally empowered body like the IMO or ITLOS to oversee or enforce operational standards in outer space. So everything right now is voluntary, decentralized, and ultimately dependent on states' own interpretations. To conclude, clarity around ISR it's not a peacetime issue. Once ISR activities directly support military targeting or command and control, the legal framework shifts from peaceful regimes of the Outer Space Treaty and UNCLOS into international humanitarian law. Ultimately, my approach is better because it reduces misinterpretation and accidental escalation. If states have transparent pre-mission notices and maneuver logs, it becomes far less difficult to wrongly assume that an ISR satellite is directly contributing to hostilities. So, in other words, peacetime coordination strengthens wartime clarity. My framework gives operators the ability to prove that their missions did not amount to direct participation in hostilities, something that can help maintain protection under IHL and avoid satellites being misclassified as military objects. If you're curious to learn more about the broader international space law framework, I warmly invite you to the Finnish Space Law Association Space Law Workshop tomorrow at 3:30 at Klondike. Although it has been shifted, we're at the pop-up stage. Thank you very much for your attention.
Thank you for Aisha Hörtä on drawing analogies between maritime and outer space law in the governance of ISR activities. Next up would be Maragu Ero on From CIS to BRICS, Comparative Perspectives on National Space Programs and International Space Policy.
BRICS seeks to overcome this by pooling resources, sharing technology, and utilizing common infrastructure. For example, a proposed joint model for the Russian orbital station would allow each member to contribute, reducing cost while fostering scientific and engineering exchange. Joint BRICS initiative, BRICS countries emphasize peaceful space exploration, focusing on scientific cooperation and joint technology projects. Key initiatives include establishing a BRICS Space Council to coordinate joint programs, sharing satellite data research through a proposed newsletter, collaborating on a joint model for the Russian orbital station, coordinated participation in the International Lunar Research Station and other deep space projects. Key findings. In 2025, Ministerial Declaration emphasized sustainable use of outer space, satellite coordination, Rule E2 and UN institution, increasing focus on space debris, orbital congestion, regulatory coordination. BRICS Space Council proposal the proposal came from the Roscosmos. Space leaders within BRICS countries, when we look at these countries, we see Russia, China, India. So the key findings of my presentation is that KISS and BRICS show alternative models of space cooperation, emphasis on peace, sustainability, shared responsibility. Space exploration can be built trust, support, development, benefit all humanity. Thank you very much for listening to me. It was my pleasure to be here with you. Best regards and sending my warmest regards to the Finland. Thank you very much. Hello, everyone. Thank you very much for this opportunity. Is everything work now? Okay, thank you very much. So today I'm going to talk about KISS and BRICS space initiatives. Can you see my screen, or may I continue without presentation? Thank you for your passion. Okay. I'm from Turkey. I'm an attorney from Turkey. So it's a great opportunity to connect this way. Thank you very much again. So let's look at my presentation. Aim of this study, it's my research to analyze KISS and BRICS as frameworks for space cooperation, to assess how cooperation supports peaceful use of outer space, sustainable development, equality access to space technologies. Why space cooperation matters? Space governance is shifting from bipolar to multipolar. Governing challenges, orbital congestion, space debris. Overcame this by pooling resources, sharing technology. Space debris, high financial barriers, international cooperation is increasingly wide as necessary rather than optional these days. So, what is the Commonwealth of Independent States? Founded in 1991 after dissolution of the Soviet Union, observed status at UN in 1994, platform for post-Soviet cooperation includes space, science, security, economy. KISS Interstate Space Council was established to develop cooperation between the KISS member states in the field of exploration and use of outer space for peaceful purpose, and to coordinate the interaction of the member states of the agreement on the implementation of joint activities. The participants include 6 states: Armenia, Belarus, Kazakhstan, Russia Federation, Tajikistan, and Uzbekistan. The agreement to establish the Interstate Space Council was ratified by the member states in the different years. The main aim to coordinate peaceful space activities, harmonize legal and policy approaches, promote joint programs and investment, functions as a coordinating and advisory body, not as supranational authority. KISS space activities include satellite development, Earth observation, environmental monitoring, disaster management, capacity building. So here I shared some space initiative of these countries, their space agencies, information about their space agencies. It's all accessible in my presentation. I can share with any member of this symposium. So now we look at what is BRICS. Originally, it was established by the Brazil, Russia, India, China, and South Africa. And since 2023, BRICS has initiated a controlled expansions process. Additional states have been invited or admitted in phases, engaged as a partners or observers. So in 70th BRICS Summit, there was a proposal to establish a BRICS Space Council as an advisory body, coordinate joint programs, policy harmonization, broad political support. This was inspired by the KISS model. So why BRICS matters in space? High cost, shared resources, technology transfer, joint missions. It is a key topics. So emphasis on sustainability, peaceful use, governance reform, as I said before. So joint space exploration requires significant financial resources, which even developed economies find challenging to sustain independently. BRICS seeks to overcome this by pooling resources, sharing technology, and utilizing common infrastructure. For example, a proposed joint model for the Russian orbital station would allow each member to contribute, reducing cost while fostering scientific and engineering exchange. So as I said before, key initiatives include establishing BRICS Space Council to coordinate joint programs, sharing satellite data and research through a proposed newsletter, collaborating on a joint module for the Russian orbital station, coordinated participation in the International Lunar Research Station and other deep space projects. Here I shared some key findings due to limited time. Please look at my presentation soon. So there is a space leaders within BRICS. It's Russia, China, and India.
And Maro, can you hear
to
us?
conclude, what is the key findings on my research is KISS and BRICS show alternative models of space cooperation,
And
emphasis
Maragu,
on
can
peace,
you hear us?
sustainability,
Maragu Eru?
shared responsibility. Space exploration can build trust, support development, and benefit all humanity. Thank you very much for listening to me. It was my pleasure to be here with you. Best regards and warmest regards to Finland. Thank you very much.
Okay. Thank you very much, Margaret. And we are very apologizing that we had very much issues now with the Zoom, and unfortunately we didn't have your full presentation. But yes, please. So we will then share your presentation and then have it available later on. And next up, we are now going to prepare, and we will have a fireside talk with an astronaut coming up.
We got to put it on. It should be on. Okay, it seems to be on. So we are talking with Markus Wandt, astronaut from Sweden, and we go up there in a moment when we have uploaded a video over there.
Thank you.
Yeah, just come closer. He doesn't bite. Oh, we can take that. Yeah, okay. And we have two videos.
And good day for the audience here. Now we will have starting a fireside talk with the astronaut Markus Wandt. And in just a second, the stage will be yours.
Thank you so much. So I'm not the astronaut, I'm Jari Mäkinen, and we speak here with Markus, and he's looking up there and smiling like always. This conference, Space Winter Satellite Workshop, this is about new space. And Markus is a new space astronaut as well, because you were the first project astronaut of ESA, totally new kind of thing, and also flying with SpaceX or Axiom Space with their Dragon capsule, so new space in that sense as well. And it was exactly 2 years ago when you were up there in space. What do you think about that right now? Is it like a dream or think that you think daily, I wish I would be there?
Thank you. Yeah, that's a great question actually, if it feels like a dream or not. So first of all, thank you for dropping in. You are just as surprised as I am that I'm sitting here right now. And I'm dressed like this because I'm also head of strategy and technology at Saab. But now it's astronaut time. So
exactly.
And so I actually got other astronauts, comrades of mine that had been to space that told me before going that it felt distant and surreal, and that it was difficult to connect it to reality that it had been. So it's like it felt like it didn't happen.
Yeah.
So before going, I deliberately thought a lot about that, and then after being launched up to the space station, and also after coming back, I actually spent time connecting those two very different worlds, because it feels very different when you get out to space. There's so many different things for the body and for how it feels to float around and doing all that. But by thinking through that whole launch part and also the re-entry and the coming back to Earth part, it felt connected. So it feels very real. It feels very real. So it does not feel like a distant dream. It feels rather like space is very close, and it feels like I can go back tomorrow, which of course is more complicated than that. I know that, but it still feels like a place you can go just as after you have flown to a new place on our planet and been there. It feels like a part of your world, and that's the way my world, I guess, expanded as well.
Yeah. But bottom line, is it a dream right now when you see these pictures, this video like over there? Is it something that was it real really?
Yeah, it's so there are two sides of that. First of all, it's still unbelievable that I actually got to go to space.
Yeah,
but
we'll speak more about that later.
But it feels very real. So the memories are very strong, and also something that's almost strange is after a while, even though it's so different, after a while it feels very natural to be there.
Yeah.
And I remember discussing this with Laurel and Jasmine, two other astronauts who were up there at the same time. We were eating food and floating around, and I remember saying that it feels. This feels very, very natural, and it feels like there should be nothing weird coming back either to gravity, which of course was not true, because balance is off and all these things have happened. So, but it felt very natural, which is strange, because there's no. It's only at that time. It's only 611 people ever of every human being existed that's been in that environment. So there's no evolution, there's no calibration of our system biologically, there's nothing that have prepared us for that environment. Still, it works very, very good.
Indeed.
Which is pretty interesting, I think.
Sure. So you were so-called astronaut class 22,
yes.
2022. And on that year, ESA, European Space Agency, selected new astronauts. And surprisingly, in addition to carrier astronauts, traditional astronauts, they selected also your kind of mission astronauts, or what was that?
It was called.
It's
still called. Yeah, but it's actually still called the astronaut reserve.
Reserve.
So yes, exactly. And then, if you're a reserve, there is an opportunity to become a project astronaut.
What do you? Well, let's start a little bit earlier. How did you decide to apply? And where did you see an advertisement somewhere, or how did it happen?
So it was actually, I was actually at home in my kitchen, and my wife came with her phone and said, "Have you seen this ad?" and I looked at it. No, I have not, and that's pretty interesting. And of course, that sparked a lot of synapses at the same time. I was like, "Oh, this is very, very interesting." And she
especially thinking about your background, so the fighter pilot and test pilot and so on. So you had very good chances from the beginning.
Which was not my view on it, but I feel it's very related to what I was doing, since as you said, I was at the time working as the chief test pilot at Saab, so I was doing flights with fighter jets every weekend and flew. I've been flying in the Air Force. I'd been flying for about 20 years. At that time, and also been working with a lot of things. I started out as an airborne ranger in the special forces, so also had that background expeditionary-wise, and also an engineer. So there were a lot of things that kind of lined up. Or actually, when my wife read through the ad, and we read through it together, all the boxes were ticked, and then I was okay. Yeah,
send.
I should probably send this application. I was thinking there is zero. This will just not happen. But on the other hand, if I don't send this application, then I know it's zero. Then nothing absolutely will happen. So of course I should send this. I made the application and sent it in there, and here we are.
But I think that at that moment already you knew Christer Fuglesang, because
did.
he has been also connected with Saab.
Yes.
And Christer is the first Swedish astronaut. And did you call to your friend and ask that should I apply?
I did not call. Well, I called and discussed. I don't remember exactly which phase, but I did call and discuss what is the astronaut job really.
Right.
Because a lot of times, I've been through a lot of different types of jobs throughout my life, and a lot of times you have a picture of how it is, and then reality is different. Every job I've had have almost, I guess, have been awesome, but it's not been what I thought it's been. So I just wanted to know, what is this like really? What's the pros? What's the cons? What's the battle wheel? How is what is happening? How is the what do you do when you're not on a mission? How is this working really?
Yeah.
And also coming from a flight test background, I also know that it's with these systems and with this type of missions and planning, there is a lot of unpredictability. And I just wanted to see how that plays out in an organization like ESA, European Space Agency. So yeah.
Exactly. And what happened then? Then finally in that application you decided that, okay, send, and you sent it. And what happened after that? How long did you wait until, okay, come to the first test?
Well, so first yeah, exactly. So you had to write a couple of letters, and then you sent that in, and then I kind of forgot about it, I think. But then I got an email. That's about half a year later, I think.
Okay.
Half a year later, and then testing started. So then the first session down in Hamburg, where you do a lot of computer-based testing, and then after that, went home, and I remember thinking, I should have done that 10 years ago, because I was not as fast, I think, as I was 10 years ago.
But you are still young.
Very young. No, actually, in the application range, so I was not close to the top level, but I am the oldest one in my class.
Yeah.
And well, but still young though. So I did those tests and figured, okay, well, that was fun, but
let's see.
Let's see. And I also know, at that point, I knew that there were thousands and thousands. It turned out there were 22,500 approved applications that fulfilled all those tick boxes, right?
Yeah.
And then I went home, and to my surprise, a couple of months later, I got a new email to go down and do further testing, and then that kept on happening. Until I was through.
Yeah. More emails come again, and so on. What was the trickiest part? So in astronaut candidate, how the test, there were physical tests and intellectual tests and all kind of tests.
Yeah.
But what was the trickiest one?
I think so there's a lot of tests,
Indeed,
but I think the most challenging one is which was also the most fun part. And that's normally the most challenging part is normally what I think is most fun also. But that was one of the interview sessions where you have like a whole panel interviewing you on a lot of different topics and things, and there are like matter experts and there are psychologists and all type of experts. And they are really pushing you, at least me, out of my comfort zone, which is challenging.
Yeah.
And as soon as I found myself like my way back to that comfort zone, someone hit me again, and then I was out. So I'm back and forth, and it goes on for quite some time. And I remember that evening that I was, so we were several candidates doing the test every day, and we had like dinner before. Everyone was like kind of chatty, and it was all like night. Very, very good environment. Like everyone was very supportive throughout the tests, which is interesting.
Yeah.
But then after, we also had dinner, but it was just quiet because everyone was so exhausted. It was like everyone was in good mood, but very tired.
Yeah. Up to the last rounds, there were also a couple of Finnish candidates, or just one, I guess, or not the last one, but before that.
Okay.
But anyway, there were.
Yeah.
What kind of feeling was among you who were tested, so that you were competitors, or already at that stage a little bit like friends?
Very much like friends. So, which is interesting, right? Because it kind of isn't it's a competition, but I did never get the feeling of people being competitive, especially not towards the end. And I think that's a part of the selections of people that were remaining. So first it was, those 22,500, then it was about 1,300, then we're down to like 400, and then 100, then 50, then 20, or 25 or so. And when we got towards the end, when it was just, I don't know, a couple of hundred left, I would say they were all team players.
All right.
And really, really helpful. We helped each other, supported each other rather than being competitive and trying to withhold information or trying to get people feeling bad about them. No, there was nothing of that, which is very interesting. Indeed. And that's also what I see in my astronaut class now, right? People are very very much team players,
exactly.
Which is super important. Indeed. Yeah, because when you're selected to an astronaut, it's not. I would argue we should ask experts at ESA about this, but I would argue you're not selecting a group, because that group will not go to space together. You're selecting individuals that will work in any group. And that was very much the feeling I had.
Indeed.
Yeah.
Before going to space, there was, of course, that little event in Paris where you were finally selected.
Yes.
I remember we met over there, and you looked a little bit sad because you were not selected as a carrier astronaut, but just a reserve astronaut. How did you feel over there when you got the information that, okay, I got the second place?
Yeah, did I look sad, or was that your expectation?
Oh, could be.
Because
you know better.
But I'll tell you though, very transparently, how that felt.
Yeah.
So rationally, first of all, I was very surprised that a guy in his 40s from Sweden was selected. To be honest, it was just not. Also during the selection, I kind of got the signals that this is not gonna. Anyway. So I was very, very positively surprised. And then before going to Paris, and I only found out that I would even go to Paris just a few days prior to, right? So there were all these secrets around it, and hey, you're going to come to Paris. And I honestly didn't know fully what that meant.
Yeah.
But I did know that there was the reserve program and it was the career program.
Yeah.
And that had been announced during the selections. That was all out there. And so the likelihood of going to space is, of course, a lot higher if you're selected as an astronaut. But it's not 100% sure.
Yeah.
There's no guarantee that you will go. So many things can happen, right? And depending a little bit on what you come from and how that works, and how the finance and all that, how that works. So the big rational part of my brain said, you know what, it's probably a lot better if you're in the reserves, and then hopefully,
it turned out to be like that.
If it could be, if there is a mission, which is highly unlikely, but maybe then that could happen, but then of course the emotional side of me, well, of course you want to be selected as a career because you're in this test, you're doing your best, and that's kind of, as you said, the first place. So of course you want to be selected as. So it was I remember when I was told, okay, so it's going to be the reserves, and I was very much expecting it, and rationally I knew-ish, I don't know if that's a defense mechanism or not, but I kind of knew that was better, maybe, or I thought that was better.
And
but I, of course, wanted to go to the other.
Yeah.
So, yeah.
Yeah.
So
Finally, it turned out to be a good idea.
Because, it was great.
Because you were the first astronaut from that group to fly 2 years ago.
Yeah.
And the first carrier astronaut will fly now next month, very likely.
Yes. So
Sophia
great.
over there. So you managed to gather money and the political will to fly 2 years ago.
Yes.
And because we have only 10 minutes to go, so I'm not asking how it happened, but when you got the information that, okay, now it is confirmed and I can fly.
Yeah.
Yeah. Did you were on a seventh sky already then?
I remember when I allowed myself to think, and this happened really fast, all of it, but still, when I allowed myself to think that this might actually happen, that was a good second. And I also told, again, my wife was there, and she actually popped a bottle of champagne, and I still have the cork. She actually painted it when I was on orbit. She actually painted it as an astronaut. So I got it when I got back to Earth. I got it. So,
okay.
Yeah. So that was fun. But then everything happened really, really fast. So within a couple of weeks, I had to hand over to the deputy chief test pilot because I was going, right? And,
yeah, exactly.
And then also changed the geothermal pump system we have at home because I knew that might break down next winter and all that, and then moved to Houston. And that happened in a couple of weeks.
Indeed.
And yeah.
When comparing the training of Axiom Space to the traditional training of astronaut, of course it is much quicker and it is more general. But what kind of training it was?
Yeah, so this is also fun being the first guy going through this, and this has changed a little bit, and I think it's going to still evolve. Axiom is facilitating and coordinating. The training, specifically in my case, is done with NASA, ESA, and then a little bit of JAXA for that module on the ISS as well. Yeah. But the general training when it comes to the how to live on orbit, how to be on the space station. And SpaceX, of course. Yep. So SpaceX for everything Dragon, how you get into the spacesuit, how you live in Dragon, and how you operate on Dragon in nominal cases and in emergency cases. Yeah.
And then in emergency cases, I think it took a lot of time.
That takes a lot of time. Yes, and then so that's up and down. That's SpaceX. And then on the space station, that's generally NASA. For space station, how to live on the station, how to use the station in general as a habitat, and then when it comes to the payloads and the science and the research and how to the work, let's call it the work, that was mainly ESA in my case.
Yeah.
So so I did a little bit a different track from the Axiom. So this was the first time that ESA uses Axiom to get Europeans to space.
Yeah.
A new way of, as you alluded to, a new way of getting Europeans to space, to increase that frequency and increase our presence there. And Axiom was actually a great facilitator to coordinate and make all this work in a really good way and in an efficient way and expeditiously. But then I have to say, ESA, when I got to European Space Station, to Astronaut Center first for the training, I'd been there a couple of times just for some not real training, just more acquaintance to the business. ESA was very fast in adapting and increasing the bar and then compressing the training, so we got so much training done in those 8 months, which was and I had quite a high ambition, a lot higher than ESA from the start, but then in the end ESA even increased that ambition, so we got all the way through the training.
Yeah, we could go on with this for hours, but we have only a couple of minutes left, so let's fast forward now to Cape Kennedy and 18th of January 2022 launch.
Yeah.
How did it feel?
Well, so
after creep and nothing, because it is exactly.
So you get into, first of all, when you walk out and you look down on those 70 meters of rocket, or 65 point something, and then you, this video flies through my brain real fast, where I see the fuel and the oxidizer being released, and the molecules meeting each other, releasing all that energy through those 9 Merlin engines, creating 7.6 meganewtons of force, and then, well, you see it there, and then pushing us up through the atmosphere. And just thinking about that gave me a lot of butterflies in my stomach, which was great. And then I got into the vehicle, lay down, and I have the countdown here. And at 1 minute, it's an auto sequence, and then when you have, I remember when I had 9 seconds left, I was thinking single-digit seconds until we go. And then we get to 5 seconds, and I remember there that a thought went through my mind, like, okay, I have the training for if everything goes okay. I have the training if it's wrong in 1 alpha, 1 bravo, or 2 alpha bravo, which are all these phases, and I know what to do. So, and if it goes totally crazy, it's not my problem anymore. So I'm just gonna relax and absorb, and that's what I do. So when it hits 3, I remember just, if you just relax your muscles, you almost can't feel your body anymore. So that's exactly what is happening. And then 2, 1, 0, and then the force, the acceleration. And I expected it to be, there's a lot of mass that's going to start moving. I expected it to be a little bit hesitant and start like vibrating, and then we start moving. But it starts right away. It just starts moving right away. And then the acceleration, if you take a fighter jet, and I've been flying that a lot, right? Take that out, go out and fly, preferably low level, cold air, so a lot of dense air. and then you light afterburn, you get this acceleration spike, which is great, a good kick in the back. But then it starts coming down, and after a while, you're at max speed, so no more acceleration. Here, a rocket is different. So it starts, it's not the same kick, but it starts. It's a very decisive force. You can feel that there's nothing in the world that can stop this motion. And then the acceleration starts to increase and increase. And then the acceleration starts to accelerate, which is a crazy feeling in itself. And that just keeps on going. So my brain, and I had not thought about this, so I was surprised, honestly. But my brain is just screaming that it's going so fast. And that's why I have this big smile during the launch, because it's...
but you are smiling always.
It's an awesome ride, yeah, at that time as well. And then you get up to 80 kilometers and ish, and then you have MECO, so main engine cutoff, and then they separate, and the booster go back and land, which is crazy in itself. And then the second stage started, and you get that acceleration going again. And that acceleration is a lot more violent than vibrations on the second stage.
Already.
Yeah, and then after about 9 minutes, you're at your 27,000 kilometers per hour, and you have second engine cutoff, and you're in space, and you can just open and float out and look at Earth. I recommend that ride. It's awesome.
Zero gravity.
Zero gravity.
A little bit more than awesome. So that go on. How does it feel? Before that, you participated already to parabolic flights.
No, I did not. We had
that.
to take that out. So it took a couple of a couple of things in the training that was not very necessary.
So it was a first touch of weightlessness.
Well, so I've actually been flying parabolic a lot of times before, but not.
Yeah.
Yes.
So how did it feel?
How did it feel? It's very, very harmonic or relaxing or very. It's just. So the first couple of days or the first couple of minutes is weird. The first couple of days you're trying to be efficient moving around, which sometimes some reflexes comes back, which doesn't make sense. If you want to turn around, you can't do this because there is no friction. You're not attached to anything. You have to counter that, right? Yeah. And also remembering first, so I turned upside down right away because it was fun. And when I did that and then turn around, it was like my brain had seen that I was turning upside down, but my body had not felt it. So when I turned around, my brain kind of intuitively expected to see this, while what I saw was this. And that kind of had to stitch the image, which that went away after, I don't know, less than an hour, but it was very strange and very interesting.
But finally you learned to be over there quite quickly and do this kind of acrobacy over there. But did you have any space sickness?
No, I did not. No, I was lucky. Yeah, I didn't. And I also had a very deliberate program to be to quickly learn how to fly without, like in the up there. So I'd made a program before going actually with, okay, I'm going to do this, I'm going to do that, and then I'm going to figure out how to do this. And that's the first couple of days I spent some time when I didn't have to work, or between actually going back and forth getting tools and things, to just learn how to maneuver, which was good, I think.
Yeah,
and you become efficient. Yeah,
for sure. Did you have some negative feelings up there, or some problems, or something like that? You didn't have any space sickness, but was there some issues?
No real issues. The only, like, the negative feeling. So after, I don't remember, a few hours after launch, or maybe a day after launch, it took us a good day and a half to get up to the station.
Yeah.
I remember a feeling of being very, very far away from my family.
Right.
I have felt that feeling before when I've been deployed to the war in Libya, or when I've been deployed to different places, right? And I've had that feeling of being far away from my family. But this was stronger than before, and we couldn't communicate at that time. You can on ISS, we couldn't from the Dragon at that time.
Exactly.
But what I did was exactly what I always do when that happened. I split. So I'm thinking about what I think that reason for that feeling of emptiness is kind of a feeling of emptiness, and why that was, and I think that was because of non-ability to communicate with my family, maybe, which I'm used to be away from, but this was different. So I I just figured, okay, when I'm on ISS, I can communicate with them. So, and we'll be there at that time. And then I just divided that whole part up to ISS. Okay, so the next step to get to ISS, that's going to be to open up this food and eat that food. And then we'll do this, and then we'll do that. And then all those things I'm doing becomes very positive because they're bringing me towards, and then all that emptiness goes away.
Exactly.
So that was a thing that was there for a few minutes, but it was enough to write it down in my diary, like, okay, this is interesting because this is really a strong feeling of being very far away and the emptiness.
We got to wrap up quite soon
Yeah.
now, but talking about food, traditionally astronauts, they are bringing something from their own country to space as well. What was the Swedish delicatessen that you brought up to the space station? Surströmming?
I should have brought surströmming. Then ISS would have deorbited a lot
Yeah,
earlier.
exactly.
So, no, I actually brought gingerbread is one of the things. It was around just after Christmas.
Ah, right, yeah.
There were a couple of things that I also tried to bring but couldn't get through. So that's one of the consequences of being the fastest trained astronaut ever is that some of the other things just don't track time-wise. But I did bring gingerbread and some other specific Swedish sweets like licorice and things that you also like here in Finland, which I'm happy for. Yes.
Yeah, and coming back.
Yes.
Then you had after 3 weeks of zero gravity, you had again the gravity.
Yeah.
It wasn't a long duration mission, but still you felt that
Yes.
1G is quite a lot.
Yes, definitely. Actually, during the re-entry, already at 0.5 Gs, I'm feeling like I'm really pressed down in the seat. And then at 0.9 G, so it's less than we have now. If we would be at 0.5 now, we would feel like we're floating out of the seats. But I felt like pushed down into the seat. And at 0.9, I remember saying to the rest of the crew, hey, try to lift your arms and head. And it feels like, compared to in a jet, it feels like about 5 Gs when you're at 0.9. So that recalibration, and that was not because of, I would argue that it's not because of loss of muscle, which happens also, right? But we do exercise a lot of there. So it's more a recalibration. Like that was my sensation in a way that there's a lot more signals needed to make this motion with my arm right now. So you kind of had to deliberately think, okay, lift the arm to lift the arm. So that was interesting.
Indeed, yeah. Would you like to fly again, or you have now selected a director path and goodbye to space flights, or is it still your dream?
I would fly tomorrow if I would get a chance.
Right.
Yes, absolutely.
Good. Okay, thank you so much. We are already a couple of minutes over.
Yes.
Thank you, Markus.
Thank you.
And
thanks for listening.
And yeah.
Yeah. Thank you.
And if you want to watch a little bit videos more at the European Space Agency sites, they have a lot of videos about Markus. And also Rymdstyrelsen has a very nice chat that he had with ESERO Sweden from space, men det är på svenska.
Oh, yeah, det är bra träning.
Yeah.
That's good
Tack så
practice.
mycket,
Okay. Thank you. Thanks for having me here.
Yes. Thank you yet again for a very nice fireplace talk from Markus Wandt. So then we will ready it up soon. Yes. Okay. So question is yes. Thank you very much today. So how do you want to be microphone? Do you want to be at the booth? There is a booth also, or do you want to handheld microphone or a headset? Microphone on? And for the next, we will now have our last track for today. And there will be 5 different presentations. And this last track will be started by Philip Paulson. And the stage is yours.
If it doesn't work, there we go. All right, hello everyone. My name is Philip Paulson. I'm CEO of IceCat. First of all, I'd like to thank Markus Wandt for the ramp up towards my talk here. You know, it was quite exciting with astronauts, but the real main event is, of course, ground-based radars. So I'm representing IceCat. We're a bit of a strange organization. I'll give you a hint about what that means. We're a government-owned startup, so with 5 decades of operations. So I'll try to give you a view of what that means in the coming slides. So IceCat is an organization that is dedicated for operating radars for scientific research, ionospheric science. We were founded back in the 70s as an association between a number of countries. So initially it was West Germany, UK, France, Sweden, Finland, and Norway. They came together and realized that in order to basically catch up with the US, they needed to put their heads together and their money together in order to invest into major infrastructure in order to enable the scientific area of ionospheric research. And since the 70s, it's been operating very, let's say, in its own corner of the space business, I would say. It's major investments into infrastructure that has basically upheld an entire scientific area on its own. It's one of the most renowned, let's say, infrastructures for ionospheric research and solar terrestrial physics worldwide. But inherently in radar-based operations, let's say over time, the rest of the world has changed a bit. So there was a decision in 2023 or so to start forming to start managing this in a different way and reforming this into a government-owned company instead of an association. So I'll give a bit of overview of what that means and why that is. So to begin with, we are a state-owned company owned by 3 countries. So it's Sweden, Norway, and Finland. Also here, we are not owned by, usually the state-owned companies are under the Ministry of Finance or Ministry of Enterprise or that, but we are straight under the Ministry of Education and Research, let's say in the different countries. And in Sweden and Finland, we are under the Research Council. So already there, we are sticking out a bit. We have a board of directors that are specifically handpicked for, let's say, our mission, which is to provide science services. So in Sweden, for example, you'll recognize Anna Ratzman, the former Director General of the Space Agency and Chair of the ESA Council, is our chairman of the board. Same then we have representatives from the Norwegian and Finnish government that are in the research area and infrastructure area. In addition, we have a number of advisory groups that are formed from our members. So we have an associate forum set up by national nominees from our membership countries. We have a scientific advisory committee that guides us on scientific strategy. Which investments should we do? What are the new hot topics in ionospheric research? Those type of things. And then we have a quite large user base for IceCat that has built up over the last 5 decades or so. So in effect, what we are doing here is that this is the decision body. These are the bodies that provide advice to us. So it's a bit of a strange setup, but the reason for this is primarily what we do. Radar-based observations have become a bit sensitive. The amount of satellites in orbit, let's say, what we do is that we detect electrons from 50 kilometers to 1,000 kilometers. From time to time, there's a satellite flying by where we're looking, and as you can imagine, we can see it pretty clearly. As an effect, you need to have, nowadays, quite a lot of processes, procedures, and ways of working in order to handle that type of sensitive data. But in addition, this is a map showing where we are located. So we are, I wouldn't say even a Nordic company in that sense, we're more of an Arctic company. Our most southernmost location is Kiruna in Sweden. And we operate large-scale infrastructure in Norway, Sweden, Finland, and in Svalbard. Our associate members, those are really the countries that fund operations. They put in money every year for investments, but also to gain access to the system. They're Norway, UK, Finland, Japan, and Sweden. So those are the current setup of associates. So this is a rather sped up thing showing what we actually do. So this is our VHF and UHF systems that we have that we operate in Norway at Ramfjordmoen. So these are transmitting and receiving units. You can see the aurora passing by. So what we do in effect is that we transmit encoded radio frequencies, VHF, UHF, and look for very faint echoes in different parts of the atmosphere. So we send, and then we simultaneously listen in the legacy system, as we call it. We used to listen in Kiruna and in Sodankylä in Finland, in order to create the, let's say, volumetric measurement in a certain area of the atmosphere. And this was done and is done. Our core mission is really to provide research based on this, ionospheric research, so looking at variations of electron densities, ion densities, those type of things. Atmospheric science, so neutral atmospheric science, looking at more climate-related effects, lower than the ionospheric or than the ionosphere. And then, of course, solar terrestrial physics, so the interaction between the solar wind and the Earth's atmosphere, and also meteor science. As a government-owned company, we are shifting a bit. Our core mission will always be science, but we are looking for new areas to apply the knowledge and the infrastructure. Some of the things that we've identified is, of course, space debris tracking, satellite tracking, launch vehicle tracking, but in addition, we have a long heritage of actually developing radars and operating them. So we are currently in a very interesting phase when we are, in addition to our core mission, setting up also commercial services where we can supply data to commercial companies, to governments, to authorities, those type of things. And now I will basically show you a bunch of infrastructure, but because this is really what we do, so that you get a feeling for these type of systems. So this is our VHF system that we operate in Ramfjordmoen. This is transmit receive. As you can see, it's rather big infrastructure, 120 by 40 meters. You can get a sense of the scale there. There's a regular door up on the transmit bridge, let's say. Roughly 3 megawatts. The same thing for the UHF system that we operate. These are 32-meter dishes. So really big systems, really big infrastructure. That's also why it's, let's say, quite closely connected to government programs in order to fund these things. In addition, in Norway, to this system that you see here in the foreground, we have what's called a heating system. This is usually what, in some, let's say, dark corners of the internet, they think that we control the weather and the minds of all the people. But that's not the case. At least we haven't managed that yet. But this is a heating facility where we can manipulate, let's say, a volume of the atmosphere. And in that sense, manipulate it in a certain sense, heat it up, and look at the effects simultaneously with our radar systems. This is a unique capability in the world. You've probably heard of HARP, which is a US equivalent, where they can heat the atmosphere, but they cannot look at the actual results at the same time. They don't have a radar connected to it. In addition, we operate systems in Svalbard. And this is, of course, becoming a bit of a hot topic with regards to more geostrategic questions. But We operate one 32-meter dish, which is steerable. We have one field-aligned 42-meter dish that used to look towards the magnetic pole. Unfortunately, it has moved a bit. So we are planning to perhaps nudge it a little bit. We'll see. But these are also big systems, very strategic location for us. But as I said, we are in a bit of a transition, not only going from an association to a company, but also through a technological shift. So some of our poor personnel have had to lead projects of tearing these landmark systems down. So our receivers that were in Kiruna and Sodankylä are now no longer. They're already gone. We are in a process of also shutting down systems in Ramfjordmoen, but we are currently managing it so that we overlap with our new systems. And our new systems are the most advanced radar in the world, on the civilian side at least. So we are shifting the technology from old, let's say, single beam systems, steerable dishes, to phased array, software-defined beamforming antennas. The project is called IceCat 3D. It's been going on for since, I think it was started back in 2007, which goes to show that it's a rather complex thing to develop a large-scale phased array radar. But it is a radar system that is also tri-static. We shift from, instead of, let's say, one antenna, we have at each site tens of thousands of antenna elements that we can individually control. We control the phase shift in between them. So the principle is pretty simple. By controlling the phase shift, you can actually steer the entire array instead of having a mechanical steering. We can do this by software. This also gives very new opportunities for us. Instead of looking at one direction, we can all of a sudden we can look at the entire sky instantaneously or virtually instantaneously. So we can create volumetric measurements of the entire field of view at basically all altitudes as well. So that means that we can study not only large-scale things that goes on in the ionosphere, we can catch quite a lot of different things flying over over northern Scandinavia. So it will be unique in a sense, this system. We will be able to give you a context, let's say from a satellite tracking point of view, instead of having consecutive measurements by ground stations, we can in one measurement basically get all orbital parameters with rather high accuracy. So it's a novel system also in that area. And just to give you an update, as I said, it's been going on for a long, long time. We are now at the stage where we have our sites built. Here you can see the transmit-receive site in Norway, in Skibotn. First stage, we will be having a transmit capability of 3.3 megawatts. One of the main things also going, let's say, from a company or into a company is that we are, let's say, we're moving away from a way of working which is, let's say, more academic into a way of working which is more industrial. So taking these online, in previous years we've always been saying our first light is next year, and all the scientists have been eagerly awaiting. What we're doing now is that we're saying a slightly more conservative view, but we're getting this system online in a smaller scale. Our intent is that for our own engineering purposes, we have all the systems online mid-2026. Towards the end of 2026, we hope to get our associates in to start doing basic research with this system. In addition, we have our site in Sweden. That's our receive site. As you can see, it's slightly smaller. We have 55 or 54 of these antenna units, as we call them, connected to each other. And the same goes in Finland. So with that said, the real purpose of me being here is really to just inform that we are now a state-owned company. This is a Swedish infrastructure, a Norwegian infrastructure, and a Finnish infrastructure. And we will put a lot of effort into coordinating between Sweden, Finland, and Norway in these areas, not only on the science side, but also let's say, SSA, SST, those type of things. So with that said, I think I'm done for this presentation. All right, thank you.
Thank you very much for Philip Paulson on ASCAT 3D, Next Generation Space Radar in the European Arctic. Thank you very much for your presentation. And next up for the next presentation is from Petri Väisänen, and it will be about Finnish astronomy and ESO, giant telescopes and technology projects. And the stage will be yours. You can leave it as is. So.
Okay, thanks very much. Hey, thanks for coming. And so yes, I'm Petri Väisänen from Finka and Turku, University of Turku, and I'll talk about what Finka is and what ESO is in a moment, and what we do, and then towards the end of the short presentation also on why are we here, because most of the stuff what we've been hearing and what this workshop is looking down, right? Or even when looking up, like you were just talking upper atmosphere. Now we are looking way, way, way past that into the universe. So, but there's a connection, and I'll get to that. But first of all, what ESO is. So we have a booth there, and I've explained a few times over this couple of days. ESO is similar to ESA, European Space Agency, that's more familiar to most of you as the type of an organization, an international treaty-level, government-level organization that Finland is part of as well, headquartered in Germany, quite a big one, 300 million operations budget annually, but the infrastructure, the telescopes, so we do, or ESO does ground-based astronomy, they're all in Chile. And you can see the reason why. If you just look outside, it's not worth if you want to spend hundreds of millions or €1 billion on a telescope. You don't want to put it in Europe. No, too many clouds. You want to put it in Atacama Desert, where it's always clear. And that's where the infrastructure is. And I'll mention more details in a moment. But that's what ESO is. And indeed, well, okay, there's a map of member countries all over Europe. Finland joined about 2 decades ago. But yeah, so it's a science organization, research organization, but doing technology development. So ESO builds its telescopes, the science instruments, together with big consortia around Europe, and that's part of the connection why we're here, and training as well. And since I'll be more talking about the science and technology, just one slide on the training aspect for especially any younger people, students, early career people, in the audience. ESO has a very, very effective, very nice program for both postdoc fellows and students, and all of these are both in the science track and technology track as well. So people in engineering can join these, cutting-edge, global cutting-edge projects in either Germany or Chile, or then either in the engineering track or science track. So for those of you in that stage in life, keep an eye on these opportunities. And ESO as a whole, yeah, I mean, how many is that? 1, 2, 3. 3 of the past 10-year physics Nobel Prizes were based on data from ESO telescopes. Everything from the discovery of the accelerating universe to detection of the first exoplanets in the 90s, supermassive black hole a few years ago. In fact, that picture on on the left there, that has a special meaning for me because I'm nothing to do with the science itself, but I just happened to be the support astronomer on VLT that night when that particular image was taken with the first adaptive optics camera on VLT. So I was there as the support astronomer, and then later on that group that I was helping got the Nobel Prize for that research. Yeah, just one slide of Finka. So this is who I represent, and Finka was established in Finland essentially to make sure that Finnish astronomers make use of ESO and that type of science. I mean, the government is paying big bucks for the membership fee, so obviously there needs to be a return. If nobody uses it, nobody gets benefit from it, why are we a member? So Finka is there to, together with 4 universities, Aalto, Helsinki, Oulu, and University of Turku, to bring that community of astronomers together to make sure that we have the skills, we train people to use ESO telescopes, get results, get that kind of cutting-edge research done, and well, make Finnish science known in the world in this area. And in addition to the research, yeah, I mean training, of course, there as well. So we support postdoc students, and then the big thing is to get into these big consortia that are building the technology for the telescopes and the instruments. So we try to coordinate that in Finland, and part of the reason why I'm here today and in this conference is also to get contacts with the industry, related industry. I'll come in a little bit moment to that technology overlap. Even though these are telescopes, these are not satellites, but there's a connection. Okay, a few pictures of the sites. So this is their crown jewel at the moment. VLT, very imaginatively named, very large telescope. So this was established 25 years ago about, the Paranal Observatory in Chile. And it's really dry. It just looks like Mars. There's nothing. You pick up a rock and there's nothing underneath. You know, you pick up a rock anywhere else, there's some bugs, nothing there. And yeah, that's what it looks like up over there. Okay, don't get me started on these lasers because I could talk about them for the next half hour. Come talk to me about the adaptive optics of these laser technology, how you correct for the atmosphere. With these telescopes, you essentially look through the atmosphere as if it's not there. Yeah, using this really cool technology. But no time to go to details there. So that was optical and infrared astronomy that VLT does. But then there's submillimeter, so radio astronomy essentially. ALMA, Takama Large Millimeter Array, built at 5,000 meter altitude, very high up. And I've met several of you actually here over these last 2 days who've been to the site. So especially the Aalto University Metsähovi group here have good connections with this research done. ESO does that, and what we really do is, in astronomy, you want to combine the wavelengths, optical, infrared, X-ray, radio. The best science comes in multi-wavelength. And, okay, in that respect, there's the new upcoming development with ESO is going to gamma rays as well. So there's a method of detecting the Cherenkov radiation from very fast-moving particles hitting the Earth, resulting from gamma rays from celestial objects. And there's a big CTAO, so Cherenkov Telescope Array Observatory, being built, both the north side to La Palma in Canary Islands and the south side very close to where VLT is in Chile, and ESO will be operating that. And okay, so then moving to the upcoming massive project. So now we had the VLT, and now the next is the extremely large telescope, ELT. So by the way, some of you probably know that in between here there was a project also called the OWL, the overwhelmingly large telescope. That was not funded. It was a little bit too big, technology was not there, so we still need to wait for the OWL. But okay, we're now at the extremely large telescope stage. Yep, by far the world's largest telescope is under construction there, and the Takama site. 39-meter primary mirror, and with Finnish participation, as I'll just mention. Yeah, this is expensive, again, 1.6 billion euro thing. You don't want to build it somewhere where you have rain and clouds to deal with. And built of, I was just chatting earlier today with somebody, we were comparing, like, so the biggest kind of Nordic telescope, optical telescope, is of the size of 1 point something, I forget exactly, 1.4, 1.5 meter size mirror. There's 800 of that size mirrors there. So there's about 800 segments, each 1.4 meters. So it makes up almost a 40-meter primary mirror. And that's a mock-up of what it would look like beside the Giza pyramids. So it is really huge. It's massive, and it's taking shape. So these pictures are probably a couple of months old now, but just from the webcam taken from the ELT website. Yeah, so it's coming up. The mirror is not there yet, but the structure is there already, and should be starting operations in 4 years or so. Okay, there's telescopes gather light, science instruments do something with it, and there's several under construction, and one of them that we have a participation in Finland is called Mikado. And yeah, so it's a multi-AO adaptive optics imaging camera. And yeah, just to get an idea, I mean, the cutting edge of astronomy right now, observational optical infrared, is the James Webb Space Telescope. And this thing with ELT, with Mikado, will be 5 or 6 times better resolution, sharper images than what JWST can do. And yeah, so we actually involved with the AO part, but more on the software development side. And the picture there, if you look at the right column, that shows what a certain patch of sky will look like with Mikado compared to on the left, there's Hubble Space Telescope image, big pixels, that's the resolution. With the middle one is the best one what we can do nowadays with JWST, and ELT Mikado on the right. So you really peer into things that we've never seen before with this resolution and size. And it's really important that we're part of these consortia, because that gives us front row access to when the telescope gets turned on, so to speak. You know, the windows open for the first time to something that humanity has never seen. We get to be there when that happens because we're part of these instrument building consortia. So the first science, kind of the cream of the crop science, gets done by these guaranteed time observing teams. There's another instrument we're part of, Mosaic, with Helsinki, Turku, Finka partnership, spectroscopy, multi-object spectroscopy. And yeah, okay, I won't have time to go much more into details, but we're just planning on what our exact hardware contribution there will be. Yeah, so ELT will open up things in the universe that we've just never seen. So anything from the first stars and first galaxies right in the early universe to looking for exoplanets, Earth-like planets around stars, inhabitable zones. So like I always tell kids or even undergrad students, when I was a student, we only knew about the planets in our solar system. Why wouldn't there be others? But we didn't know. Now we know, because the VLTs and others have found the planets in the Milky Way. It's teeming with planets, but we still don't know what's on them. We don't know if there's atmospheres, if there's water, da-da-da. But the next generation will get to there. So this is where the ELT generation of technology will come in. It's just a slide of very many different kinds of science that can be done with the ELT. And okay, coming to an end, ESO is already talking about the next generation. What happens after ELT? This is the massive science project of today, still to be completed, but we already, it takes 10, 20 years, the cycle of coming up from an idea to actually build something. So we now need to be thinking what we want to do in the 2040s. So there's a program started already now. The astronomy communities is canvassed for ideas for expanding horizons, astronomy in the 2040s, and specifically European astronomy in the 40s, transformational decisions to be made in probably a couple of years now, deadlines for these proposals sometime next year, 2027, and we have to be part of this. Finland has to be part of this. These are massive technology projects, not only science projects, but technology development projects. And the earlier we get into the slipstream of these projects, the better. And it's just starting now. So that's part of the reason why I'm here as well, hopefully to catch people who can build things, can build exciting stuff. And speaking of that, essentially my last point here, why are we as a ground-based observatory, why did I come, why did we come to this conference where it's mostly more about satellites and stuff? It's because there's a huge overlap in technology with the space sector. So, yeah, not an exhaustive list whatsoever. I just kind of at the top of my head, earlier this morning, I listed some areas where I know that we do similar things. Anything from adaptive optics, extremely sensitive detectors, wanting to push technology. I mean, in our case, you want to see the last photon from the faintest objects in the universe and do it very stably and safely, shielded, radiation-shielded things, very high precision pointing tracking systems because everything is moving. I mean, one example there is this extremely stable calibration systems, laser stuff, where we move 30 kilometers a second around the sun, solar system is moving 250 kilometers per second around the Milky Way, everything moves. But with these exoplanets, we're detecting movements of 20 centimeters per second. So out of the movements of hundreds of kilometers per second, you want to tweak out walking speed. So the calibration methods have to be really, really, really sensitive and precise. So a lot of these things are very similar to what people are doing in space tech. It's easier for us to fix things if something breaks down, of course, but otherwise. Okay, and I'll finish over there with just an invitation to be part of technology development. This is really exciting science projects. Thank you very much.
And that was Petri Väisänen with Finnish Astronomy and ESO giant telescopes and technology projects. And next up it will be Vladislav Bezrukov's VIRAC, a dual-purpose radio astronomical facility for space mission support and solar ionospheric research. And please, the stage is yours.
Hello, thank you for the introduction. I will continue ground segment section, and my talk will be about IRBERE, or VIRAC, Ventspils International Radio Astronomy Center, radio telescopes, and how we can be used for satellite community as well. And hope it works. Yeah, where we are and who we are. So we are neighbors of Finland, and we are located in Baltic Sea coast. And as you see here in the picture, I don't know. Yeah, here is nice Baltic Sea coast in a forest. And our two main instruments is RT32, 32 meters antenna, and 16-meter antenna seen here, and new phased array LOFAR. And as you see here, so this is nice red lights of our antenna. We hide in the forest, and this was actually done with purpose. And we, as an institute, a part of Ventspils University of Applied Sciences, and Ventspils here, university is here, but we are around 30 kilometers in a forest. Similar situation is Aalto and Metsähovi. And we are quite new as an institute. We are 30 years old only, but our history starts in the 50s. when Soviet secret base was established in Ventspils region with 3 telescopes. No, actually 2 survived and 1 was dismounted. And in 60s, this telescope was built. And in 1994, when Soviet army gone, these telescopes was not used, and our Academy of Sciences decided, okay, we take it to our needs, but they was so destroyed, so telescopes stay on place, but not movements, no controls, nothing. It takes a lot of efforts and years to make these telescopes working, and first scientific lights we got only in 1998, so after 4 years with efforts of improving these telescopes. After that, our center, VIRAC, joined in this time Ventspils University College, and in next, like our milestone, 2 institutes, Institute of Research, Engineering Research Institute and Ventspils International Radioastronomy Center merged together, combining engineering skills and radioastronomical skills, and now we are so long name. And in 2019, we make next improvement of our facilities. We built and launched LOFAR station, Latvia. And you see here how it looks. And probably we was lucky enough to make a number and name of this LOFAR, and this LOFAR station clearly seen from satellites. This is part of LOFAR network distributed to all Europe. So it's international LOFAR network. Nowadays it's LOFAR ERIC. And we working in 2 regimes, providing data and observations for LOFAR ERIC itself, like international network, and working as a single station doing ionospheric and solar studies. Our main instruments, parabolic antennas, so you see here, like RT32, 32 meters antenna, and RT16, 16 meter antenna, and it took, again, as I told, a lot of efforts to improve these antennas from being like a old, like a garbage, but now it's fully functional antennas. And maybe good, like a heritage from these antennas. These antennas was built for spying, and they're extremely fast. So it's not like a normal radioastronomical antennas, but it's antennas dedicated for satellite movements as well. And as you see, RT16, it's like a 5 degrees per second, so it's very nice and like a fast and sensitive instruments. Both these antennas are participating in science studies in European LBI network. Again, it's a so it looks like it's European network, but in reality now it's global LBI network combining antennas all over the world. Our observatory contributing to this network in 4 subbands, so 1.6, 5, 6.7, and 8.4 gigahertz. Again, both antennas participating in like a availability status. So if mostly it's RT32, but sometimes RT16 as well. But we also use our opportunity to use 2 antennas, not like a independent single stations or interferometric network, global interferometric network, but we provide and use these antennas as a single baseline radio interferometer, like a local interferometer, doing galactic maser monitoring, AGN variability, and sometimes also GNSS-based observations and satellite and space debris positioning research and studies, and searching for stellar flares as well. So this is like a quite unique opportunity to use 2 instruments on site with additional sensitivity and reduction of RFI. Currently, so these antennas all time we try to improve and add additional equipment, and I will say why my talk called dual use. So first of all, of course, it's a scientific instruments and we use it for science. But nowadays we understand to use these antennas as much as possible, we need provide additional services. And we do a lot to provide ground services for satellites as well. These antennas, so RT52, at this moment, we have, so this is warm ambient receiver L-band, 1.6, and this is a cryogenic one, S6 band receiver. So this is our main instrument at this moment. Cryogenic receiver, so it's inside vertex room. You see it's dual and electronics. So it's divided in 4 sub-bands. You see here like a 2, no, here 4.5, 5, 6, and 7. So we're able to observe at 1 gigahertz regime for each sub-band. L-band receiver is not so complicated, but again, it's like a first version of our homemade receiver. And you see here it's 1.4 up to 1.7 gigahertz. Again, working for GNSS sometimes and for science cases. Additional, quite unique instrument what we are operating for RT52 is a low noise spectral polarimeter. So this is how it looks and how it looks installed in telescope. So it's instrument from 4 up to 14 gigahertz, specially dedicated for solar observations. And our telescope beam size is rather small, and we are able to map a sun in radio bands and how it looks sun from our radio telescope. This one is 4.6 gigahertz and beam size like this one, and we're able to like a map a solar surface, and similar map but higher frequency disappear. It should be 12 gigahertz, same like a image but more detailed structures. So just one example how it could work together. But as you see in previous slides, we are rather limited with equipment, so we are able not to put new receivers. And last years, we were working hard to improve our vertex room, and now vertex room, it looks like this one. So we have a lot of place for new instruments and new receivers and transmitters as well. And just for comparison, so it's like a telescope and vertex room with only one receiver system, CX band. And now, after reconstruction, so we reduce a bit like a size of a surface. So we sacrifice surface, but now we have a lot of places for new receivers. And exactly now, engineering group are working hard to prepare new systems and put it inside. And additionally, our secondary mirror made so it's possible to move it and make receivers offset observations. So it's a tuned system for offset observations. And here is some nice pictures from last autumn. So it's first transmitters installed in our system. And from last year, both antennas actually able to not only use like a passive system, but also equipped with up 2 kilowatts transmitting power. And main goal to be compatible with NASA LEX requirements and provide S, X, and K band transmitting system capabilities, both for RT32 and RT16. And main intention, of course, to work with this lunar and Mars mission, which will arising now, and help with LEO missions for CubeSats and any other services. So now it's possible, and we are already 3 years operating as a ground station on downlink regime, and now acquiring licenses to make it uplink as well. And similar refurbishment and improvement occurring for RT16, and idea is to make it XKK feed system, dual band, so, and transmitting and receiving. And at this moment, again, here is model, but it's not only model. Now we have also a physical system. So it's a cryostats for X and K for RT16. And in laboratory, it looks like this one. So, and colleagues testing at cryogenic temperatures. So it's around 13 to 12 Kelvins. So it's technically should operational. And idea is, again, so this would be services what we could provide in addition for science cases, what we are doing now. And we already have put, so this is a Swedish Space Corporation ground stations map, and you see Latvia here. So this is our Irbene site, which is marked in this map, and we're collaborating with SSC as a ground station in dual use. So I think this is all what I would like to say, and thanks for listening. And here is all my colleagues involved in these works as well. Thanks a lot.
Yes, thank you very much for Vladislav Bezrukov's. It was about VIRAC, a dual-purpose radio astronomical facility for space mission support and solar ionospheric research. And next up, we will have Bela Dixit, and the presentation will be about Metsähovi Radio Telescope Digital Backend Upgrade. And you feel ready?
Hello?
Yes.
Am I audible?
Okay.
Hello? Yeah. Hi, I am Bela. Doctoral student at the Aalto University and working with Dr. Kai, Dr. Talwiki, and Dr. Thomas. So today I'll talk about the digital backend upgrade for the Metsähovi triple band receiver. So further going into detail, I will first give you a short introduction about the Metsähovi. So, okay, so Metsähovi, it's a 14-meter radio telescope. It's a parabolic dish with a Cassegrain focus when located at Kirkkonummi, Finland. It has been observing for the 50 years. Last year only we celebrated the Metsähovi's 50th birthday. So it used for the single dish observation as well as for the VLBI observation. And it's mainly observing like active galactic nuclei. So it's like a long-term observation of monitoring of the active galactic nuclei. So the Metsähovi currently has two types. So working on currently has a single dish receiver at 22 gigahertz, 37 gigahertz, and VLBI receiver at 22, 43, and 86 gigahertz. These all systems are working fine, but they are limited by the narrower bandwidth, high receiver temperature, and there are a different hardware chain for the single dish and VLBI. So all these limitations affects on the sensitivity and efficiency of the telescope. So to overcome these limitations, we are upgrading the system. As a part of upgrade, Metsähovi ordered a new triple band receiver. So this receiver is capable to observe simultaneously at the 3 bands, K band, Q band, and so K band is ranging from this one. Hello? Yeah. K band is ranging from 18 gigahertz to 26 gigahertz. Q band is ranging from 34 to 50 gigahertz, and W band is split into 2 parts, W1 and W2. It's ranging from 80 gigahertz to 116 gigahertz. This is the 3D view of this receiver. You can see there are 2 beams, and inside the cabin there are some horn antennas and a dichroic mirror. So it has this cryogenic cooling system, Also, it is capable to observe in the full polar mode, and the same receiver can be used for the single dish as well as VLBI observation. So this new receiver has very less receiver noise temperature, and it has very high bandwidth. So these two factors directly affecting on the sensitivity, it improves the sensitivity of the telescope. So the current system has this, in a single dish mode, has this receiver noise temperature is 270 and with the new receiver, you can see this blue line. This is the new receiver. Sorry. Hello. Yeah. Thus at 37 gigahertz, thus usually the sky temperature is 50 Kelvin. Thus with the current system, the total system temperature is 330 Kelvin for the 37 gigahertz band. But with the new receiver, it's dropping from 33 to 90 Kelvin. So it's like a 3.5 factor of 3.5 improvement in the sensitivity. Also, there is this the instantaneous bandwidth is increasing from 1 gigahertz to 8 gigahertz. That adds extra to approximately 2.8 factor of sensitivity. So overall sensitivity in a nominal weather condition, it's increasing around factor of 10 as compared to current receiver system. So for this, such a sensitivity comes with wider processing bandwidth. So definitely we will need the new backend system to process such a huge bandwidth, because K-band receiver has the 8 gigahertz of instantaneous bandwidth, and Q and W1 and W2 has around 16 gigahertz of instantaneous bandwidth with the two polarization and 2 beams. So total processing bandwidth is 224 gigahertz. So to process such a huge band, we will need the new backend system, digital backend system. So the basic requirement for this backend systems are simultaneously multi-processing, real-time processing for this all data, real-time processing this data and get this full stock output at the backend side, like backend output. Thus, then it should be, the hardware should be compact, because we are planning to put this backend system immediately after the receiver. So it should fit inside the Cassegrain platform. So considering all these requirements, we selected this RF-SoC-based modular structure, and we were searching for appropriate hardware which should be compact and allow us to design the carrier board around us. So we selected this knowledge resources RF-SoC board. This is the, you can see this left-hand side, there is this module. First image is this module. This is the knowledge resources module, and the second one is the knowledge resources carrier board. Currently, for the lab testing, we are using this knowledge resources carrier board, but we are building our own carrier board. This is like right-hand side, you can see this is the customized carrier board. Mainly, Kai is working on this system. So what is RF-SoC? And why we want to use this RF-SoC system? RF-SoC is a system-on-chip module, and it has the high-speed analog to digital converters. So we can directly digitize the IF band. Also, it has the large field programmable gate array. We call it as a FPGA fabric for the real-time signal processing. Also, it has the embedded ARM processor. It is really good for the monitoring and controlling purpose. So considering all this thing was inside the single module, we selected this RF-SoC based system. You can see this first part is the analog part. Mainly this is the carrier board. And the second part is the digital system part, which is inside the RF-SoC module. And mainly my PhD thesis topic is this one. So I'm building this backend system. So there are challenges because the RFSoC module has the 8 analog to digital converters, but each ADC can process only 2 gigahertz of bandwidth. But we want to process total 8 gigahertz of instantaneous bandwidth in a single board. So we are using this interleaved ADC and sideband separation technique to increase the bandwidth from the 2 gigahertz to 8 gigahertz. And we are using this Casper tool flow. Casper tool flow, it's nothing but the combination of MATLAB and Vivado, which allow us to design this firmware using graphical programming. But it does interleaved ADC and sideband separation has a bit challenging thing because all ADCs are not exactly identical. There are some offsets in a gain and phase. So we have to correct for that. Otherwise, it will directly affects on the spectral quality. So that's why we first simulated this 8 gigahertz spectrometer to see the effect of offset on the spectra quality. So we simulated it in the Python and Julia. Here you can see the spectrum. We applied the single tone signal to the in simulation and swept across the band. This tone input, like single frequency swept across the band. You can see the spectrum is pretty clear and there is no any arc effect. But as soon as we introduce a little bit offsets, there are some unwanted spikes or spoots. We call it it's spoots. So to remove this arc effect, we have to calibrate this ADC very carefully. It's like inside the system, it's like a picosecond level. We have to calibrate the system like up to 3 picosecond. So it's a bit challenging. We are working on this system. So I will end this with the summary and outlook. So new triple band receiver has the total 224 gigahertz of processing bandwidth. So definitely we will need the new backend system. And to implement such a huge bandwidth processing system, we selected this RFSoC-based modular structure, which allowed us to implement this wideband polarimeter inside the small box, like small module. So this, and basically we tested this all techniques, like all algorithm inside simulation. Also did some basic testing on the RFSoC module, like hardware testing, like basic ADC calibration with a single ADC, not interleaved ADC, but single ADC and other stuff. What is the next step then? The next step is like calibrate all ADCs with the new carrier board, then implement the full polarimeter, and integrate this backend system with the new triple band receiver. We are expecting this receiver by the end of September this year. So yeah, that's all. I would like to thank all my Metsahovi and Finca colleagues. Also, I would like to thank ERC because this backend development project is funded by ERC. Also, I would like to thank all my collaborators and all other funding agencies. Thank you. Thank you.
Thank you, Bela Dixit, about Metsahovi Radio Telescope digital backend upgrade. And for the last presentation of this track will be from Hannu Koivula, and it will be about Genesis, Mission and Space Geodesy, future contributions from Metsahovi Geodetic Research Station, Finland. And please, Hannu, stage is yours.
Okay, thank you very much. I'm a professor of geodesy in the National Land Survey of Finland in the Finnish Geospatial Research Institute. And so I'm geodesist, so I'm interested in measuring the size and shape of the Earth. And I'm working in the National Land Survey, so we are interested in creating coordinate systems where you like to relate all your Earth observations. So I start from the observatory side, and then we lift up a little bit to the space as well. And thank you for the previous presenter for the little introduction of the Metsähovi. We are neighbors. Our observatory is just maybe 100 meters from the Aaltos Observatory in Metsähovi. So the content of the presentation is that I will give you first the introduction for the reference frame, so the coordinate system where everything should work on Earth, and Earth orientation parameters. Then I introduce the infrastructure that is used for creating such systems, so Metsähovi Geodetic Research Station and all the other similar stations. Then we come to the Genesis mission and what is the contribution to the reference frame. So we talk about the reference frame. The reference system is a definition of the coordinates, so how the X, Y, and Z are on the Earth. It's a terrestrial because the coordinate system rotates together with the Earth, so you should basically get the same coordinates every time when you measure at the same point. When we have a reference frame, we realize this definition to the Earth, basically to the observatories like Metsähovi or the permanent GNSS stations. So we do have a coordinates, X, Y, Z coordinates for these places, and the change rates, how fast these coordinates are changing, due to plate tectonics, due to land uplift, or whatever. And this is a frame where all the remote sensing data should be expressed. This is the frame where all the satellite positioning should be done. Actually, all satellite positioning systems are tied for this EITRF coordinate frame. This is the most accurate available in the world. And our Metsähovi Geodetic Research Station is part of the global network defining the system. Another important aspect is the Earth orientation parameters, because our interest coordinates are in the rotating Earth and don't change. But the satellites are in the celestial reference system that doesn't have a clue how the Earth is rotating under it. So if you want to relate the coordinates to the Earth, you need Earth orientation parameters, and we use these geodetic observatories to measure this. So like this, all the satellites need to know how the Earth is spinning under it to relate the observations to the Earth, to the right coordinates. Our infrastructure is like, one important one is a very long baseline interferometry, so we use the radio telescopes, like the Aalto University as well. Yours is bigger, ours is faster. So ours is 12 degrees per second, it's super fast, these new Vigos telescopes. So we are observing the signals from the quasars. Our observing session, typically we are measuring like 60 different quasars from different directions with all the available radio telescopes at the same time. And then we correlate the data and we can start measuring the Earth orientation in space in the system defined by the quasars. Another instrument is satellite laser ranging. In Metsähovi, we have a kilohertz laser, so we are shooting like 1,000 pulses per second. The pulse energy is something like 2 millijoules, and length of the pulse is something like roughly 10 picoseconds. So we are shooting the satellites which have retroreflectors, so they are reflecting the signal back. So we can then measure the distance and evidently also the orbit. So we can define the orbits of the remote sensing satellites. But there's also satellites which are meant for the geodetic purposes. They look like a disco balls. They are only covered with the retroreflectors. They are rotating the Earth in the gravity field of the Earth, so they are rotating around the mass center of the Earth. And when the global network is measuring these satellites, we can define where is the mass center of the Earth, which is important for the coordinate reference frame because that defines the origin of the coordinate system. Third important set of the instrument is the DORIES instruments, which are actually sort of reverse of the satellite GNSS satellite positioning. So they are sending signal up and the satellites are having the receivers, and they are using the Doppler effect for defining the orbits of the satellites or the location of the receiver. And the fourth one is the GNSS, Global Navigation Satellite System. And in that case, we are measuring the coordinates daily, every day, of all these sites. And from time series, we can see like the land uplift, how the plates are moving, etc., etc. So this is a summary. This is like all the parameters we like to define for the coordinate system and Earth orientation parameters. All different instruments have benefits of, they are good in measuring something. But our goal in the global geodetic observing system is to reach accuracy of 1 millimeter on coordinate level and a change accuracy better than 0.1 millimeter per year. This has an impact because this system is used when the orbits, for example, for the remote sensing satellites are defined. And if you are using like several missions for observing, for example, sea level, you need to be sure that these orbits are in the same reference frame and you are measuring the sea level change, not the small rotation of the coordinate system. So that being said, it's important to co-locate all these instruments. You saw the networks earlier that there was like something like 50 SLR stations, 50 VLBI stations. But when you are looking at the network where all these are in the same location, there's only a couple of stations who fulfill the scenario. And these are really important stations for reaching the goal of 1 millimeter accuracy and long-term stability of 0.1 millimeter. And most of all this work is actually done by the scientific organizations. It's mainly in the IAG, International Association of Geodesy, that has services for all these different instruments. They are collecting the data, analyzing the data, providing the products, for example, providing the Earth observation parameters that I would say most of the satellite missions are using these products made by the scientists. Then shortly, only picture about our site. Our neighbor is not visible, it's a little bit on the right, the ALTA telescope there, but we do have all these four. So we have a radio telescope, 13 meters. We can receive all the frequencies between 2 to 14 gigahertz. Our satellite laser is there, GNSS is there, and then the door is beacon a little bit aside, a couple of kilometers aside, because we don't want to have sending radio frequencies close by the radio telescope because it disturbs the observations. And now we go to the Genesis mission. We lift up the Metsähovis or these observatories to the orbit. Genesis mission is ESA mission where in the one satellite there is a VLBI sender, so they are sending the data in the same frequencies that this VLBI telescope can receive. They have a GNSS receiver, they have a satellite laser ranging reflectors, they have a DORIS receiver. So basically they have all instruments in one satellite that these observatories have. The latest value, what I know, because there has been quite several different validations or simulations, which is the best scenario for the mission. But as far as I know, the latest numbers are the height of the satellite will be 6,000 kilometers, inclination 95, orbital period 3.8 hours, and it will be launched 28 or 29 is my estimate, something like that, in a couple of years. And in Metsähovi, we also are just finalizing our VLBI and latest version of the SLR this year, so we will be ready when the mission is ready. The goal of the Genesis mission is really targeted for this goal of 1 millimeter accuracy for terrestrial reference frame and 0.1 millimeter accuracy for in time. And this is a one-day ground crack with this inclination of 95, how it would look. And from Metsähovi perspective, from our radio observatory, if the mission would be up and running, this is the orbits what we would have seen today. So it's very well visible at Metsähovi observatory. So the major sort of an impact, or the, I would say, what I like to say here is that the Finland has one of the best equipped geodetic observatories in the world. There's just few stations that have all these instruments in the same location. So we are in a unique situation there. And then when we have a Genesis, it has all these instruments at one. It connects it. And as you know, like the radio telescope, it's not like a mass production equipment, nor is the satellite laser racers. They are all individual. So there is some issues in creating the terrestrial reference frame of some biases between the observatories which are not solved. And from my perspective, the major improvement that Genesis can bring is that it has an accurate space tie that we know where the signal comes from or what we are measuring, so it helps us to pinpoint the biases on the observatory level. And this way, it will help us to reach the 1 millimeter accuracy goal. There's still challenges to be solved, mainly about this calibration of the antennas, because all these antennas need to be calibrated so that they are better than 1 millimeter accurate local tie on the satellite level. So it's not only that we know that how far they are from each other, we need to have like a phase center offsets, and we need to have a phase center variations of these antennas for all the different directions so that we can really use these for calibrating our geodetic sites, observatories. This is really like a mandatory to really have an improvement. And who will then benefit? This is my last slide of the Genesis. So it's basically anybody who is using space missions or the measuring the coordinates or any location-based information on Earth. It starts from the geodetic infrastructure. If we can make the biases smaller, what we are having at the moment, we will get the better coordinates. We have get the better orbits, more precise mass center of the Earth. It leads to the better orbits for the altimetry satellites, which leads to the better estimates of the sea level change, for example. You can just go however you like to go this table. But anyway, this will lead for the more reliable, with smaller uncertainties, measurements of the Earth and a better long-distance, long-term stability. That was the last slide. Thank you.
Yes, now we have at least one microphone still working. So that was Hannu Koivula, and it was Genesis Mission and Space Geodesy, future contributions from Metsähovi Geodetic Research Station, Finland. And thank you all here for today who are still being here on the Kaleva stage. And now this track has ended, so thank you for your attendance. And what we have, at least from the program, there should be in 10 minutes a poster session right here behind. And soon, I guess, there will be more information following. But really, thank you all here, and thank you for the last track and your attention.